Hello, dear listener. Welcome back to our quiet corner of the universe. I'm so grateful you've chosen to spend this time with me tonight. We're about to embark on a journey into the deepest mysteries of reality itself. Tonight, we'll explore quantum physics, not the intimidating equations or complex theories, but the profound wonder of discovering that beneath our everyday world lies something far stranger and more beautiful than we ever imagined. Before we begin, I'm genuinely curious. Where in the world are you listening from right now? And what time is it where you are? I love imagining all the different places and moments we're sharing together. Here's a confession. I've been thinking about quantum physics for decades, and I still get a little dizzy when I really contemplate what it means. Tonight, you might too, but in the most wonderfully soothing way possible. If you find yourself drawn to these gentle explorations of science and mystery, please consider giving this video a like or subscribing to the channel. Your support helps me continue creating these peaceful journeys into wonder. So find your most comfortable position. Let your breathing slow. Allow your mind to drift with me as we shrink down into the hidden worlds that exist within every atom, every particle, every moment of existence. The universe is about to whisper its deepest secrets to us. Let's begin our journey by imagining the book beside your bed, or perhaps the phone in your hand. These objects feel solid, permanent, reliable, but if we could somehow shrink ourselves down, not just a little, but by impossible amounts, we discover that this solidity is mostly an illusion. Picture yourself getting smaller. First, you might shrink to the size of a grain of sand. The book beside you would now tower like a mountain range, its pages like vast cliffs. Keep shrinking. Now you're the size of a bacterium, and the fibers of the paper look like enormous logs scattered across an endless landscape. But we're just beginning. Shrink down to the size of a large molecule, and those paper fibers become like massive tree trunks. The space between molecules starts to reveal itself, vast, empty distances that make the book seem less like a solid object and more like a sparse forest, with enormous gaps between the trees. As we reach atomic scales, something magical happens to our understanding of matter. That solid book isn't solid at all. It's made of atoms, and atoms are mostly empty space. If an atom were the size of a football stadium, its nucleus would be like a marble sitting at the center of the field. The electrons would be tiny specks orbiting somewhere in the upper reaches of the stadium. Everything else, the vast majority of the atom, is simply empty space. Now comes the truly remarkable part of our journey. We're going to shrink down to see individual atoms, to understand just how small an atom is. Imagine this. If you could line up atoms side by side, it would take about 100 million of them to stretch across the width of your fingernail. That's not 100 or 1,000 or even 100,000, but 100 million atoms, each one a complete world unto itself. This means that you, right now, are mostly empty space. The chair you're sitting on is mostly empty space. The ground beneath you, the air around you, the stars in the sky, all of it is mostly emptiness, held together by invisible forces. It's as if the entire universe is made of ghost-like structures that somehow create the illusion of solidity through their intricate dance. But here's where the story becomes even more enchanting. These atoms that make up everything around you aren't just tiny solar systems with electrons orbiting like planets. That's the old picture, and it's beautifully wrong. The reality is far more mysterious and wonderful. This is our first hint that we're entering a realm where the familiar rules of everyday experience simply don't apply. In our world, a ball is either in your left hand or your right hand. But in the atomic world, something can somehow be in both places at once, existing in what scientists call a superposition of states. As we shrink down to truly atomic scales, we discover that electrons don't orbit the nucleus like planets around the sun. Instead, they exist in something called electron clouds, fuzzy probability zones, where an electron might be found. It's as if the electron is somehow spread out, existing in multiple places simultaneously until something forces it to choose a specific location. The atoms in your body, the atoms in the air you breathe, the atoms in the most distant stars. They're all playing by these strange, wonderful rules. They're all participating in a cosmic dance that follows logic so different from our everyday experience that it seems almost magical. As we prepare to venture even deeper into this hidden reality, take a moment to marvel at what we've already discovered. You are not separate from this atomic world. You are this atomic world. Every breath you take, every heartbeat, every thought passing through your mind right now is the result of countless atoms following their mysterious quantum choreography. The boundary between you and the universe around you, which seems so clear and definite, is actually a shimmering, dancing interface between countless quantum systems. You are not just observing the quantum world, you are the quantum world, temporarily arranged in the beautiful, complex pattern that experiences itself as you. Now, we must shrink even further, diving into the heart of the atom itself. Here, in the nucleus, we encounter the first truly mind-bending mysteries of quantum physics. To understand this density, imagine taking Mount Everest and somehow compressing it down to the size of a sugar cube. The material inside an atomic nucleus is thousands of times denser than that. A teaspoon of nuclear material would weigh about as much as a mountain, yet this incredibly dense core sits at the center of mostly empty space, like a tiny sun in a vast hollow universe. The nucleus of an atom is unimaginably small, yet it contains nearly all of the atom's mass. If that atom were our football stadium, remember, the nucleus would be like a marble at the center. But this marble is not simple. It's made of even smaller particles called protons and neutrons, packed together so tightly that the density defies everyday comprehension. But protons and neutrons are not the end of our journey into smallness. They too are made of even smaller particles called quarks. And here, dear listener, we encounter something that sounds like poetry, but is actually precise science. Quarks have names like up and down, strange and charm, top and bottom. These aren't just whimsical labels. They represent different types of these fundamental particles, each with its own personality and behavior. A proton, for instance, is made of 2 up quarks and 1 down quark, bound together by the strong nuclear force. A neutron contains 1 up quark and 2 down quarks. These quarks are held together by particles called gluons, which carry the strong force between them. The name gluon comes from gluon, and indeed, they act like the universe's strongest adhesive, binding quarks together so tightly that no individual quark has ever been observed in isolation. Here's where our journey takes a turn toward the truly mysterious. These quarks and gluons don't behave like tiny billiard balls bouncing around inside the proton. Instead, they exist in a constant state of quantum flux, popping in and out of existence, creating virtual particles that live for impossibly brief moments before disappearing again. Inside every proton in your body right now, there's a bubbling quantum soup of particles appearing and vanishing faster than thought itself. The proton's mass doesn't even come primarily from the quarks inside it. Most of it comes from the pure energy of this quantum activity, converted to mass according to Einstein's famous equation E=mc². As we explore these subatomic realms, we discover that the very concept of particle starts to break down. These aren't really tiny spheres or points of matter. They're more like knots in the fabric of quantum fields, patterns of energy and probability that we call particles because our minds need something familiar to grasp onto. Each type of particle is actually an excitation in its own quantum field. The electron field permeates all of space, and what we call an electron is just a ripple in this field. The photon field gives rise to particles of light. Even the Higgs field, which gives other particles their mass, fills all of space with its invisible presence. This means that the empty space around you isn't empty at all. It's filled with quantum fields, all of them vibrating at their lowest possible energy states. Sometimes these fields get excited and create particles. Sometimes particles interact with the fields and disappear. It's a constant dance of creation and annihilation happening everywhere, all the time. These quantum fields are so fundamental that they exist even in the vacuum of space, far from any stars or planets. Even if you could somehow remove every particle from a region of space, the quantum fields would still be there, humming with their zero-point energy, occasionally fluctuating enough to create virtual particles that flash into existence for infinitesimally brief moments. The electrons orbiting in the atoms of your body are constantly interacting with these quantum fields. They're absorbing and emitting virtual photons, borrowing energy from the vacuum and paying it back faster than the universe can notice. This isn't just theoretical, it's measurable. These virtual particle interactions actually affect the energy levels of electrons in ways that scientists can detect with incredible precision. As we prepare to dive deeper into quantum mysteries, pause for a moment to consider what we've discovered. You are not just made of atoms, you are made of quantum fields playing out their eternal dance. Every particle in your body is constantly being created and destroyed, borrowing energy from the vacuum, interacting with invisible fields that permeate all of space. The distinction between matter and energy, between particle and wave, between something and nothing, all of these familiar boundaries begin to blur when we look closely enough. We're about to explore how these blurred boundaries lead to some of the most beautiful and confounding discoveries in all of science. We've journeyed down through the scales of size, from books to atoms to subatomic particles. Now we arrive at a threshold, a boundary not of space, but of understanding. This is where the familiar world of classical physics simply stops working, where the rules that govern baseballs and planets and falling leaves no longer apply. Classical physics is beautifully deterministic. If you know the position and velocity of a baseball, you can predict exactly where it will be at any moment in the future. Newton's laws work perfectly for objects we can see and touch. But as we shrink down to quantum scales, something remarkable happens. The universe becomes fundamentally uncertain. The threshold isn't marked by a sign or a gateway. It's more like walking from a well-lit room into a realm where light itself behaves differently. This boundary appears when we reach what's called the Planck scale. Distances so small that even the concept of space begins to break down. At everyday scales, we can measure things with perfect precision, limited only by the quality of our instruments. But at quantum scales, the universe itself places fundamental limits on what can be known. This isn't because our instruments aren't good enough. It's because measurement itself becomes an act of disturbance, like trying to determine the exact position of a soap bubble by poking it with a stick. The quantum threshold is where we discover that the act of observation changes what we're observing. In the classical world, you can look at a baseball without affecting its motion. But in the quantum world, the very photons used to see a particle carry enough energy to nudge it into a different state. It's as if the universe is fundamentally shy, changing its behavior whenever we try to peek at what it's really doing. This threshold is also where the concept of definite properties begins to dissolve. In our everyday world, a coin is either heads or tails, but quantum particles can exist in what's called superposition. They can be in multiple states simultaneously until the moment of measurement forces them to choose one state or another. Imagine if you could be in multiple places at once, walking through several different rooms of your house simultaneously, only collapsing into a single location when someone called your name. This sounds impossible, yet it's exactly how quantum particles behave. They exist in fuzzy probability clouds, spread across multiple possible states, until interaction with the larger world forces them to manifest as definite, measurable properties. At this threshold, we also encounter the breakdown of local realism, the idea that objects have definite properties independent of observation, and that influences can't travel faster than light. Quantum particles can be entangled in ways that make them instantaneously connected across vast distances. When you measure one particle, you immediately know something about its partner, even if that partner is on the other side of the galaxy. This isn't just theoretical speculation. Scientists have performed countless experiments that confirm these quantum effects. They've created particles that exist in multiple states simultaneously. They've demonstrated instant connections between particles separated by large distances. They've shown that the act of measurement really does change the behavior of quantum systems. The quantum threshold is also where time itself begins to behave strangely. In classical physics, time flows uniformly from past to future. But in quantum mechanics, particles can tunnel through barriers instantaneously, appearing on the other side before they've had time to travel there. Some interpretations of quantum mechanics suggest that quantum events might even influence their own past, creating loops of causality that defy common sense. Perhaps most mysteriously, this threshold is where the boundary between possible and actual becomes blurred. Classical physics deals with what is, definite states, precise positions, determined outcomes. But quantum physics deals with what might be probability waves, potential states, multiple possibilities existing simultaneously, until reality is forced to choose. As we cross this threshold, we must leave behind many of our intuitive notions about reality. The idea that objects have definite properties, that causes precede effects, that things are either here or there, but not both. All of these assumptions must be gently set aside. Yet here's the beautiful paradox. Despite existing in this realm of uncertainty and superposition, quantum particles somehow conspire to create the stable, predictable world we experience. Billions of uncertain quantum interactions average out to give us the reliable behavior of larger objects. Here's the beautiful paradox. Despite existing in this realm of uncertainty and superposition, quantum particles somehow conspire. It's as if the universe uses uncertainty as a tool to create certainty, employs randomness to generate order. Standing at this threshold, we realize that we're not just studying physics, we're exploring the fundamental nature of reality itself. The quantum realm isn't just a smaller version of our everyday world, it's a completely different kind of existence, one that challenges our deepest assumptions about what it means for something to be real. Light has been humanity's greatest mystery and most faithful companion. It warms our faces, illuminates our world, and carries information across vast distances. Yet light itself defies our most basic attempts to understand what it actually is. As we prepare to step across this threshold and explore the specific phenomena of quantum physics, take a moment to appreciate where we are. We're about to enter a realm where the impossible becomes routine, where mystery isn't something to be solved, but something to be experienced, where the universe reveals itself to be far stranger and more wonderful than we ever dared to imagine. But other scientists, particularly Christian Huygens, argued that light behaved like waves. Waves could explain how light bent around corners, how it created the beautiful interference patterns seen in soap bubbles, and how different colors could be understood as different wavelengths. When light passed through narrow slits, it spread out in patterns that looked exactly like water waves spreading through a harbor entrance. For centuries, scientists debated whether light was made of particles or waves. Isaac Newton, with his towering genius, argued that light must be composed of tiny particles, what he called corpuscles, streaming through space like invisible bullets. This made intuitive sense. Light travels in straight lines, casts sharp shadows, and bounces off mirrors just like a ball bouncing off a wall. For a long time, these seemed like mutually exclusive possibilities. Something couldn't be both a wave and a particle. That would be like saying the ocean was simultaneously made of water and tennis balls. Yet quantum physics revealed that light is indeed both, depending on how we choose to observe it. When we design experiments to detect light as particles, we find particles. These particles of light are called photons, and they behave remarkably like Newton's corpuscles. They carry discrete packets of energy, they can knock electrons out of metals, and they travel through space as localized bundles of electromagnetic energy. But when we design experiments to detect light as waves, we find waves. These waves exhibit all the properties that fascinated earlier scientists: interference, diffraction, and the ability to be characterized by wavelength and frequency. Red light has a longer wavelength than blue light, just as you'd expect from a wave phenomenon. The truly mind-bending aspect is that light doesn't somehow choose to be a wave or a particle. It is both, simultaneously. The wave nature and particle nature aren't separate properties that compete with each other. They're complementary aspects of a single deeper reality that our minds struggle to grasp. This duality reveals something profound about the nature of reality itself. The universe doesn't always fit into the neat categories our minds create. Sometimes, the most fundamental truths require us to hold seemingly contradictory ideas simultaneously, to embrace paradox as a feature of reality, rather than a problem to be solved. Think of it like this. Imagine trying to describe a three-dimensional sphere to someone who can only perceive two dimensions. Depending on the angle of observation, the sphere might appear as a circle, an ellipse, or a straight line. None of these two-dimensional projections fully captures the three-dimensional reality, but each reveals a true aspect of the sphere's nature. Similarly, the wave and particle descriptions of light are like two-dimensional projections of a higher dimensional quantum reality. When we observe light in ways that reveal its wave nature, we're seeing one projection of this reality. When we observe it in ways that reveal its particle nature, we're seeing another projection. The complete quantum reality encompasses both. The wave-particle duality of light also suggests that the act of observation plays a fundamental role in determining what we see. It's not that light is sometimes a wave and sometimes a particle. It's that our method of observation determines which aspect of its nature becomes apparent to us. This has profound implications for our understanding of the relationship between consciousness and reality. If the act of observation determines what we see, then observers, including conscious beings like ourselves, might play a more fundamental role in shaping reality than we ever imagined. When we use detectors designed to catch individual photons, we interact with light in a way that reveals its particle nature. When we use detectors designed to measure wave properties, like interference patterns, we interact with light in a way that reveals its wave nature. The universe responds to our questions by emphasizing the aspect of reality that our question is designed to reveal. The wave-particle duality of light also hints at the deeper unity underlying apparent contradictions. Waves and particles seem opposite. One is spread out and continuous, the other is localized and discrete. Yet light shows us that these opposites can be unified at a deeper level of reality. As you drift towards sleep tonight, consider the light that gently illuminated your evening. Every photon that reached your eyes was simultaneously a wave and a particle, carrying within its quantum nature the deepest mysteries of existence. The last light you saw before closing your eyes was a messenger from the quantum realm, whispering the secret that reality itself is far more beautiful and mysterious than our everyday experience suggests. Perhaps this teaches us something about existence itself. Maybe the contradictions and paradoxes we encounter in life, order and chaos, being and becoming, unity and diversity, aren't problems to be resolved, but complementary aspects of a deeper truth that encompasses both. This discovery began with a young French physicist named Louis de Broglie, who in 1924 proposed something that seemed almost absurd. If light, which we think of as a wave, can behave like particles, then perhaps matter, which we think of as particles, can behave like waves. His idea was so radical that even he wasn't entirely convinced it was true. Just when scientists thought they had begun to understand the strange dual nature of light, the quantum realm revealed an even more astonishing secret. Matter itself exhibits wave-like properties. The solid, tangible world around us, including your own body, is fundamentally made of waves. But the universe, as it often does, proved to be more imaginative than even the most creative scientists. De Broglie's matter waves turned out to be beautifully, measurably real. Every electron, every proton, every atom in your body has a wavelength associated with it, just as real as the wavelength of light. The wavelength of matter depends on its momentum. The faster something moves, the shorter its wavelength. For large objects like baseballs and people, the wavelength is so incredibly tiny that we never notice the wave-like behavior. But for tiny particles, like electrons, the wavelength is large enough to create observable effects. Electrons orbiting the nucleus of an atom don't follow definite paths like planets around the sun. Instead, they exist as standing waves, like the vibrations in a guitar string. Just as a guitar string can only vibrate at certain frequencies that create harmonious notes, electrons can only exist in certain wave patterns that create stable orbits. This is why atoms are stable, and why chemistry works the way it does. The electrons in an atom exist in what scientists call orbitals, three-dimensional wave patterns that describe where the electron is likely to be found. These aren't tracks that the electron follows, but rather probability clouds that show where the electron wave is most intense. The shapes of these electron waves determine how atoms bond with each other, how molecules form, and ultimately how life itself is possible. The double helix of DNA, the proteins that make up your muscles, the neurotransmitters in your brain, all of these complex structures exist because electron waves can only take on certain patterns, creating the regular, predictable behavior we observe in chemistry. But here's where the wave nature of matter becomes truly mind-bending. Electrons can interfere with themselves, just like waves in water. Scientists have performed experiments where they send individual electrons through two slits, one at a time. Each electron somehow passes through both slits simultaneously, creating an interference pattern with itself. This isn't just a theoretical curiosity. It's been demonstrated with increasingly large molecules. Scientists have shown wave-like behavior in molecules containing dozens of atoms. They've even demonstrated interference effects with molecules so large they contain hundreds of atoms. It isn't just a theoretical curiosity. It's been demonstrated with increasingly large molecules. Scientists have shown wave-like behavior in molecules containing dozens of atoms. The boundary between the quantum world and the classical world isn't as clear-cut as we once thought. With the Powell theory attained theory seminary. With theory seminary. The wave nature of electrons also gives rise to one of the most practical applications of quantum physics, the electron microscope. Because electrons have much shorter wavelengths than visible light, they can be used to see details far smaller than any optical microscope can reveal. The stunning images of viruses, cell structures, and even individual atoms that have revolutionized biology and medicine are all possible because electrons behave like waves. This isn't just a laboratory curiosity. Quantum tunneling is happening in your body right now. The fusion reactions that power the sun depend on quantum tunneling. The enzymes that facilitate chemical reactions in your cells use quantum tunneling to speed up biological processes. Even the flash memory in your phone works because electrons can tunnel through barriers that should stop them. The wave nature of matter also explains one of the most beautiful phenomena in quantum physics. Quantum tunneling. Because matter behaves like waves, particles can sometimes pass through barriers that should be impossible to cross. It's like a water wave somehow, continuing on the other side of a wall, even though the wall should completely block it. But perhaps the most profound implication of matter waves is what they tell us about the nature of existence itself. You are not just made of particles, you are made of waves. Every atom in your body has a wavelength. Every electron exists as a probability cloud. Every chemical bond is the result of wave interference patterns. The wave nature of matter also suggests that consciousness itself might be understood as a wave phenomenon. Some scientists speculate that the coordinated quantum activities in your brain might create interference patterns that give rise to unified conscious experience. Your thoughts, dreams, and sense of self might be the result of matter waves dancing in the quantum fields of your neural networks. This means that the boundary between you and the world around you isn't as solid as it appears. Your matter waves extend slightly beyond your physical body, creating a fuzzy quantum interface with the environment. In the deepest sense, you are not separate from the universe. You are a pattern of waves in the same quantum fields that permeate all of space. Picture a wall with two parallel slits cut into it, like two narrow doorways side by side. When you shine light through these slits onto a screen behind them, something magical happens. Instead of seeing two bright lines corresponding to the slits, you see multiple bands of light and darkness, an interference pattern created when light waves from the two slits interact with each other. As you settle into sleep tonight, remember that you are not just resting your body, you are allowing countless matter waves to shift into new patterns, new harmonies, new possibilities. The dreams that visit you might be the result of quantum interference patterns in your brain, matter waves creating new combinations of thought and experience that would be impossible in the classical world. There exists an experiment so simple that it can be performed on a tabletop, yet so profound that it reveals the deepest mysteries of reality. The double-slit experiment has been called the most beautiful experiment in physics, and for good reason. It shows us that the universe is far stranger and more wonderful than we ever imagined. This suggests that each photon must be passing through both slits simultaneously, existing in a superposition of states where it takes both paths at once. The photon behaves like a wave, spreading out and passing through both slits, then interfering with itself to create the pattern we observe. But here's where the mystery begins. The same interference pattern appears even when you dim the light so much that only one photon at a time passes through the apparatus. Each individual photon somehow creates the same interference pattern, as if it were interfering with itself. This makes perfect sense. If light is a wave, waves from the two slits spread out and overlap, creating regions where they reinforce each other, bright bands, and regions where they cancel each other out, dark bands. It's like dropping two stones into a still pond and watching the ripples create complex patterns where they meet. But if you place detectors at the slits to determine which path each photon actually takes, something extraordinary happens. The interference pattern disappears. The moment you try to observe which slit the photon passes through, it begins behaving like a particle, passing through one slit or the other, but never both. This is perhaps the most profound discovery in all of science. The act of observation fundamentally changes the nature of reality. It's not that we're simply discovering which path the photon took. We're actually determining which path it takes. The photon's behavior depends on whether we're watching. Scientists have performed this experiment with electrons, atoms, and even large molecules. The results are always the same. When unobserved, particles behave like waves, creating interference patterns that suggest they take multiple paths simultaneously. When observed, they behave like particles, taking definite paths and creating no interference. This has led to one of the most mind-bending questions in physics. What constitutes an observation? Is it the conscious act of a human being looking at the result? Or is it any interaction with a measuring device? The answer seems to be the latter. Any interaction that could, in principle, provide information about the particle's path destroys the interference pattern, regardless of whether a human being actually looks at the result. The implications stretch far beyond physics. The double-slit experiment suggests that the universe is not made of definite objects with definite properties, but of possibilities and probabilities that collapse into definite states only when observed. This challenges our deepest assumptions about the nature of reality. This suggests that information itself plays a fundamental role in quantum mechanics. The universe seems to distinguish between situations where information about a particle's path exists, even if unread, and situations where no such information exists. Reality appears to be fundamentally about information and its availability, not just about matter and energy. Perhaps most mysteriously, the experiment suggests that the boundary between the quantum world and the classical world isn't fixed. Large molecules can still exhibit wave-like behavior and create interference patterns. Some scientists speculate that under the right conditions, even larger objects might exhibit quantum effects. The line between the quantum and classical realms seems to be more about the flow of information than about size. The double-slit experiment also reveals the complementary nature of quantum reality. We can choose to observe the wave nature of particles by not detecting which path they take, or the particle nature by detecting the path, but we cannot observe both simultaneously. This complementarity seems to be built into the fabric of reality itself. Some interpretations suggest that before observation, particles exist in multiple states simultaneously, only choosing a definite state when measurement forces them to. Others propose that measurement doesn't just reveal reality, it participates in creating it. Still others suggest that every possible outcome actually occurs, but in parallel universes that split off from our own. As you drift towards sleep, consider that the very act of your consciousness, observing your thoughts, might be collapsing probability waves in your brain, selecting specific neural patterns from a vast space of possibilities. Your dreams might be moments when this observation relaxes, allowing your brain to exist in quantum superposition, states where multiple realities coexist. The double-slit experiment teaches us that we are not passive observers of reality. We are active participants in its creation. Every observation you make, every measurement you take, every moment of conscious awareness participates in the eternal dance between possibility and actuality that defines our universe. In the quiet darkness of your bedroom, countless quantum events are unfolding, each one a miniature double-slit experiment where reality chooses its path based on the subtle dance of observation and possibility. You are not separate from this process. You are this process, consciousness itself arising from the quantum foam of collapsing possibilities. Picture a coin spinning in the air. While it spins, it's neither definitively heads nor tails. It's in a dynamic state that encompasses both possibilities. But quantum superposition is far more radical than this. A quantum particle isn't like a spinning coin that will eventually land on one side or the other. It's more like a coin that is simultaneously heads and tails, existing in both states at once, until observation collapses it into one definite state. Quantum superposition is perhaps the most alien concept in all of physics, yet it's as fundamental to reality as gravity or electromagnetism. It's the principle that quantum systems can exist in combinations of all possible states until the moment of measurement forces them to choose a specific state. Close your eyes and imagine being in your kitchen and your bedroom simultaneously, or not moving between them, not remembering one while being in the other, but actually existing in both places at the exact same moment. This sounds impossible, even absurd. Yet this is precisely how quantum particles spend their existence, in multiple states, multiple locations, multiple realities, all at once. This isn't just a limitation of our knowledge or measurement techniques. The particle genuinely exists in multiple states, simultaneously. It's not that we simply don't know which state it's in, it's that it's actually in all possible states at once, weighted by probability. This superposition isn't a brief transitional state. It's the natural condition of quantum systems. Particles spend most of their existence in superposition, only collapsing into definite states when they interact with something that can provide information about their properties. The definite classical reality we experience is actually the exception, not the rule. Consider an electron in an atom. Before measurement, it doesn't orbit the nucleus in a definite path. Instead, it exists as a probability cloud, simultaneously occupying all possible positions around the nucleus. The cloud is denser in regions where the electron is more likely to be found, but the electron is genuinely present throughout the entire cloud until observation forces it to appear at a specific location. Specific location. The mathematics of superposition is beautifully precise. Quantum states are described by wave functions, mathematical expressions that encode all possible states of a system and their probabilities. When particles are in superposition, their wave functions are combinations of all possible states, creating interference patterns that can be calculated and predicted with extraordinary accuracy. Scientists have demonstrated superposition with increasingly large and complex systems. They've created superconducting circuits that carry electrical current in both directions simultaneously. They've put tiny mechanical oscillators into superposition states where they vibrate and don't vibrate at the same time. They've even created quantum superposition states involving hundreds of particles, all existing in multiple states simultaneously. But superposition extends far beyond simple position or momentum. A quantum particle can exist in a superposition of different energy levels, different spin states, different polarizations. It can simultaneously be moving in multiple directions, vibrating at multiple frequencies, or even existing in multiple quantum fields at once. The implications for our understanding of reality are staggering. If quantum superposition is fundamental to the universe, then the classical world of definite properties and specific locations emerges from a deeper reality where everything exists in combinations of all possibilities. This suggests that the future itself might exist in superposition. Before you make a decision, all possible choices might exist simultaneously in the quantum fields of your brain. The act of deciding, of conscious observation, might be what collapses these superposition states into the specific reality you experience. Some scientists speculate that consciousness itself might be a quantum phenomenon, arising from the superposition states of neural networks. Your thoughts, emotions, and sense of self might emerge from the collapse of quantum superposition states in your brain, creating the unified experience of consciousness from the underlying quantum multiplicity. Superposition also raises profound questions about the nature of identity and continuity. If you are made of quantum particles that exist in multiple states simultaneously, then in what sense are you a single continuous self? Perhaps the feeling of being a unified individual is itself the result of countless quantum collapses, creating the appearance of consistency from underlying multiplicity. The universe revealed by quantum superposition is far richer and more creative than the classical world of definite objects and properties. It's a reality where potential is as real as actuality, where possibilities have their own existence, where the future influences the present through the probability waves of quantum fields. As you prepare for sleep, consider that your brain might be shifting into states where superposition becomes more prominent. Dreams might be moments when your consciousness experiences multiple realities simultaneously, when the normal collapse of quantum states relaxes, allowing you to exist in the fluid, probability-rich realm of quantum superposition. The boundary between sleeping and waking, between dreams and reality, between possibility and actuality, might be more porous than we imagine. In the quantum realm, these boundaries don't exist. Everything is superposition. Everything is possibility. Everything is the eternal dance between what might be and what is. In 1935, a brilliant physicist named Erwin Schrödinger proposed a thought experiment that would forever change how we think about reality. He imagined a cat in a sealed box, its fate tied to a quantum event. This wasn't just a playful intellectual exercise, it was a profound exploration of how quantum strangeness might extend into our everyday world. Tonight, as you drift into sleep, you're not just resting your body, you're allowing your consciousness to explore the vast landscape of quantum superposition, where all possibilities exist simultaneously, where the future and past interpenetrate, where you can be everywhere and nowhere, everything and nothing, all at once. According to quantum mechanics, before we open the box, the radioactive atom exists in a superposition of states, simultaneously decayed and not decayed. This means the entire chain of events exists in superposition too. The Geiger counter has both detected and not detected radiation. The hammer has both broken and not broken the flask. The cat is both alive and dead. Picture this scenario. A cat is placed in a sealed box alongside a Geiger counter, a radioactive atom, a hammer, and a flask of poison. The radioactive atom has a 50% chance of decaying within an hour. If it decays, the Geiger counter detects it, triggering the hammer to break the flask, releasing the poison and killing the cat. If it doesn't decay, the cat remains alive. This seems absurd, and that was exactly Schrödinger's point. He was highlighting what he saw as a fundamental problem with quantum mechanics. How can the strange rules of the quantum world, where particles exist in multiple states simultaneously, possibly apply to large objects like cats or hammers, or even the complex systems of our everyday experience? The thought experiment reveals the profound mystery of the quantum classical boundary. We never observe cats that are simultaneously alive and dead. We never see hammers that are both broken and intact. Yet if quantum mechanics is universally true, and if quantum superposition applies to all systems, then why don't we see these macroscopic superpositions in our daily lives? Emilius. But this raises another mystery. What constitutes an observation? Is it the conscious act of a human being looking into the box, or would a video camera recording the interior cause the collapse? What about the cat itself? Surely it would know whether it's alive or dead. This puzzle has led to various interpretations of quantum mechanics, each offering a different solution to the cat's paradox. The Copenhagen interpretation suggests that the act of observation causes the quantum system to collapse into a definite state. The moment we open the box, the superposition collapses, and the cat becomes either definitively alive or definitively dead. The many worlds interpretation offers a radically different solution. It suggests that the cat is indeed both alive and dead, but in different branches of reality. When we open the box, we don't collapse the superposition. We simply find ourselves in one branch of the multiverse, where the cat has a definite state. In other branches, equally real but inaccessible to us, the cat is in the opposite state. Some scientists propose that the boundary between quantum and classical behavior isn't about consciousness or observation, but about decoherence, the process by which quantum systems lose their coherence when they interact with their environment. Large objects like cats are constantly interacting with air molecules, photons, and other particles, causing their quantum states to decohere into classical behavior. This suggests that macroscopic superposition might be possible under the right conditions. Scientists have created quantum superposition states with increasingly large objects, superconducting circuits containing billions of electrons, mechanical oscillators visible to the naked eye, and even small crystals. The cat might remain in superposition if the box could be perfectly isolated from all environmental influences. The implications extend far beyond physics. If consciousness itself involves quantum processes, then perhaps your mind exists in superposition states, simultaneously considering multiple thoughts, emotions, and possibilities. Your decision-making process might involve the collapse of superposition states in your brain, selecting specific neural patterns from a vast space of quantum possibilities. Recent experiments have pushed the boundaries of quantum superposition to remarkable scales. Scientists have created superposition states in systems containing trillions of particles, all existing in multiple states simultaneously. They've demonstrated quantum effects in biological systems, suggesting that life itself might exploit quantum superposition for processes like photosynthesis and bird navigation. Dreams might be moments when this quantum decoherence relaxes, allowing your consciousness to exist in fluid superposition states where multiple realities coexist. In dreams, you can be in multiple places simultaneously, experience impossible combinations of events, and exist as different versions of yourself, all characteristics reminiscent of quantum superposition. As you drift towards sleep tonight, consider that you might be like Schrödinger's cat, existing in a superposition of sleeping and waking states. Your consciousness might be simultaneously experiencing the physical world and the realm of dreams, only collapsing into one definite state, when the morning light observes you and determines your state. The mystery of Schrödinger's cat reminds us that the universe is far stranger and more wonderful than our everyday experience suggests. Reality might be fundamentally about superposition, about the coexistence of all possibilities, about the eternal dance between what might be and what appears to be. The cat paradox also suggests that the boundary between life and death might not be as clear-cut as we assume. At the quantum level, the distinction between different states is often a matter of degree rather than kind. Perhaps consciousness itself exists in superposition states, simultaneously experiencing multiple realities, multiple possibilities, multiple versions of existence. In the quiet darkness of your bedroom, you are both the observer and the observed, both the cat and the person opening the box, both the quantum system and the classical world. You exist at the beautiful, mysterious boundary where possibilities collapse into reality, where the quantum realm touches the world of everyday experience. In the quantum realm, there exists a delicate dance between order and chaos, between the preservation of mysterious quantum states and their inevitable dissolution into classical reality. This dance has a name, the interplay between quantum coherence and decoherence, and it holds the key to understanding why we don't see quantum strangeness in our everyday lives. Quantum coherence is the property that allows quantum systems to exist in superposition, to be entangled with distant particles, and to exhibit all the strange behaviors we've been exploring. A coherent quantum system is like a perfectly tuned orchestra, where all the quantum waves maintain their precise relationships with each other, creating the interference patterns and correlations that define quantum behavior. Picture a quantum particle in superposition, existing in multiple states simultaneously. Its wave function is coherent. All the different components of the superposition maintain precise phase relationships with each other. This coherence is what allows the particle to interfere with itself, creating the complex probability patterns that govern quantum behavior. But quantum coherence is fragile, exquisitely sensitive to any disturbance from the outside world. When a quantum system interacts with its environment, even in the subtlest ways, it begins to lose its coherence. This process is called decoherence, and it's what transforms the strange superposition-rich quantum world into the definite classical world we experience. Decoherence happens when quantum systems become entangled with their environment. Imagine a quantum particle in superposition, floating in what seems like empty space. But space isn't truly empty. It's filled with thermal photons, electromagnetic fields, and other particles. When the quantum particle interacts with these environmental influences, its pure quantum state becomes mixed with the states of countless other particles. The timescales of decoherence are remarkably short for large objects. A dust particle loses its quantum coherence in about 10 circumflex 31 seconds, faster than any conceivable measurement could detect. For a cat, decoherence would occur in unimaginably brief moments, making macroscopic quantum superposition practically impossible under normal conditions. This is why we don't see quantum superposition in everyday objects. A cat, a table, or even a dust mote is constantly interacting with air molecules, photons, and other environmental influences. These interactions cause immediate decoherence, making it impossible for macroscopic objects to maintain the delicate quantum states necessary for superposition. The particle doesn't lose its quantum nature. It simply becomes part of a much larger, more complex quantum system that includes the entire environment. But from our perspective, observing only the particle itself, the quantum behavior seems to disappear. The superposition appears to collapse. The wave function seems to become localized, and the particle begins to behave classically. Scientists have learned to fight decoherence by creating increasingly isolated quantum systems. In quantum laboratories, researchers cool systems to temperatures near absolute zero, shield them from electromagnetic radiation, and isolate them from all possible environmental influences. Under these extreme conditions, they can maintain quantum coherence for extended periods, allowing for the study of quantum phenomena in larger and larger systems. But decoherence isn't just a nuisance that hides quantum effects. It's also what allows the classical world to exist. Without decoherence, quantum systems would remain in superposition indefinitely, never collapsing into the definite states that make measurement and observation possible. Decoherence is what creates the stable, predictable world that allows complex structures like stars, planets, and life to exist. The battle against decoherence has led to remarkable achievements. Scientists have created quantum systems that maintain coherence for hours or even days, allowing for the development of quantum computers, quantum communication systems, and quantum sensors that exploit quantum effects for practical applications. But decoherence also reveals something profound about the nature of reality itself. The classical world isn't separate from the quantum world. It emerges from it through the process of decoherence. Classical behavior is what quantum systems look like when they become entangled with their environment. This suggests that the boundary between quantum and classical isn't fundamental, it's contextual. The same system can behave quantum mechanically in one context and classically in another, depending on its level of environmental interaction. Reality itself might be fundamentally quantum, with classical behavior emerging as a special case. Some scientists speculate that consciousness itself might be understood in terms of coherence and decoherence. Perhaps conscious awareness arises from quantum coherence in neural networks, creating unified conscious experience from the underlying quantum multiplicity of brain states. The stream of consciousness might be maintained by delicate quantum coherence, while the discrete nature of thoughts and perceptions might result from decoherence events in the brain. Sleep and dreams might involve different patterns of coherence and decoherence in the brain. During deep sleep, neural networks might maintain longer coherence times, allowing for the fluid, superposition-rich experience of dreams. Waking consciousness might involve more rapid decoherence, creating the stable, classical-like experience of everyday awareness. The rhythm of coherence and decoherence might also explain the cyclical nature of sleep and waking. Just as quantum systems can be brought in and out of coherence by changing their environmental conditions, consciousness might cycle between coherent and decoherent states, creating the natural rhythm of sleep and waking that governs our lives. As you settle into sleep tonight, consider that your brain might be shifting into states of extended quantum coherence, allowing your consciousness to explore the fluid, probability-rich realm of quantum superposition. Your dreams might be moments of restored quantum coherence, where the decoherence of waking consciousness relaxes, allowing you to experience the strange, beautiful world of quantum possibilities. The dance between coherence and decoherence is happening in every atom of your body, every moment of your existence. It's the rhythm that connects the quantum realm to the classical world, the pulse that transforms possibility into actuality, the eternal heartbeat of reality itself. Quantum entanglement is perhaps the most mysterious and counterintuitive aspect of quantum physics. When two particles become entangled, they form a single quantum system, even when separated by vast distances. Measuring one particle instantly affects the other, regardless of the space between them. This isn't just theoretical. It's been demonstrated in countless experiments across distances of kilometers, and even between Earth and satellites in orbit. Albert Einstein, for all his revolutionary insights, was deeply troubled by one particular feature of quantum mechanics. He called it spooky action at a distance, and his discomfort with this phenomenon would spark debates that continue to this day. What Einstein found so unsettling was the idea that two particles could be instantly connected across any distance, sharing information faster than light could travel between them. To understand entanglement, imagine two particles that are created together in a way that their properties are correlated. For instance, two photons might be created with opposite polarizations. If one is vertically polarized, the other must be horizontally polarized. Idem means to as opten diria matter. Idem means to as opten diria matter. But remember, in quantum mechanics, particles exist in superposition until measured. So these photons exist in a combined state where neither has a definite polarization, but they are perfectly correlated. But here's the truly remarkable part. This correlation isn't predetermined. The particles don't know in advance what their properties will be. The act of measuring one particle somehow instantaneously determines the state of both particles, even if they're separated by the entire width of the universe. This correlation isn't like two coins that are always opposite when flipped. It's more fundamental than that. The particles don't have definite properties until measurement. They exist in a shared superposition state where all possibilities coexist. When you measure one particle and find it vertically polarized, you instantly know that the other particle, no matter how far away, will be found horizontally polarized when measured. When scientists finally performed these experiments in the 1970s and 1980s, they found that quantum mechanics was correct. The correlations between entangled particles were stronger than any local hidden variable theory could explain. The universe really does contain these mysterious, instantaneous connections. Einstein, along with colleagues Boris Podolsky and Nathan Rosen, proposed in 1935 that quantum mechanics must be incomplete. They argued that particles must have hidden variables, predetermined properties that we simply couldn't detect. This would explain the correlations without requiring instantaneous communication between distant particles. For decades, this remained a philosophical debate. Einstein's hidden variables seemed reasonable, while the quantum mechanical description seemed to require impossible instantaneous connections. But in 1964, physicist John Bell proved that any theory with local hidden variables would make different predictions than quantum mechanics for certain experiments. This doesn't mean that entanglement can be used to send messages faster than light, or the measurement results on each particle appear random. You can't control what result you'll get when you measure your particle. It's only when you compare results with your distant partner that the perfect correlations become apparent. Information about the correlation can't be transmitted faster than light, preserving the cosmic speed limit of relativity. Some scientists speculate that entanglement might be related to the structure of space-time itself. According to some theories, the smooth fabric of space-time might emerge from a deeper level of quantum entanglement, with entangled particles creating the geometric relationships that we perceive as distance and time. The implications of entanglement extend far beyond physics. If particles separated by vast distances can be instantly connected, what does this mean for our understanding of space and time? Perhaps the universe is far more interconnected than we imagined, with hidden quantum threads linking distant regions of space-time. Entanglement also raises profound questions about the nature of reality and consciousness. If particles can be instantly connected across vast distances, might consciousness itself be an entangled phenomenon? Perhaps your thoughts and emotions are entangled with the quantum processes in your brain, creating the unified experience of consciousness from distributed neural activity. The phenomenon extends to larger systems too. Scientists have created entangled states involving thousands of particles, all perfectly correlated despite being distributed across macroscopic distances. Sabike centizivri centizivri. Sabike 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 centizivri. They've entangled the quantum states of tiny crystals, mechanical oscillators, and even biological systems. As we explore the cosmos, we're discovering that entanglement might be more common than we thought. The radiation left over from the Big Bang shows signs of quantum entanglement on cosmic scales. The particles in distant galaxies might be entangled with particles in our own solar system, creating invisible connections that span the observable universe. As you drift towards sleep tonight, consider that you might be entangled with the quantum fields that permeate all of space. Your consciousness might be instantaneously connected to quantum processes throughout the universe, sharing in the eternal dance of correlation and connection that defines the deepest level of reality. Perhaps most mysteriously, entanglement seems to transcend time as well as space. Some experiments suggest that particles can be entangled with their own past and future states, creating temporal correlations that challenge our understanding of causality. The universe might be woven together not just by spatial entanglement, but by temporal quantum threads that connect different moments in time. The atoms in your body were forged in the hearts of distant stars, and perhaps they maintain quantum entanglement with the cosmic processes that created them. In the deepest sense, you are not separate from the universe. You are the universe, temporarily organized in a pattern that experiences itself as consciousness, forever connected to the cosmic web of quantum entanglement. Bell's theorem begins with what seem like reasonable assumptions about the world. The first is locality. The idea that objects are only directly influenced by their immediate surroundings. A particle here cannot be instantly affected by something happening far away. This seems obvious. If you move a rock on Earth, it doesn't immediately affect a star in another galaxy. In 1964, an Irish physicist named John Stuart Bell proved something that would forever change our understanding of reality. His theorem, elegant in its simplicity yet profound in its implications, demonstrated that the universe must be fundamentally different from what our everyday experience suggests. Bell's theorem forces us to abandon at least one of our most basic assumptions about reality, and the choice is both surprising and unsettling. The second assumption is realism, the idea that objects have definite properties, whether or not we observe them. A ball is either red or blue, whether or not anyone is looking at it. This also seems obvious. Surely, the world exists independent of our observations. But Bell proved mathematically that any locally realistic theory must make specific predictions about the correlations between measurements on entangled particles. These predictions can be tested experimentally, and they are expressed in what are called Bell inequalities, mathematical limits on how strong the correlations can be if the world is locally realistic. The stunning discovery is that quantum mechanics predicts correlations that violate these inequalities. According to quantum theory, entangled particles can exhibit correlations stronger than any locally realistic theory allows. It's as if the universe is more interconnected, more correlated than classical physics suggests is possible. These assumptions combined suggest that the universe is locally realistic, made up of objects with definite properties that are only influenced by their immediate environment. This is the kind of universe Einstein believed in, where everything has a definite state and influences travel at finite speeds. This forces us to give up one of our fundamental assumptions. Either locality is false, particles can be instantly influenced by distant events, or realism is false. Particles don't have definite properties until measured. Neither option is comfortable for our everyday understanding of reality. When scientists performed the actual experiments, first in the 1970s and many times since, they found that quantum mechanics was correct. The correlations between entangled particles consistently violate Bell's inequalities. The universe is not locally realistic in the way we intuitively expect. Most physicists accept that locality is violated in quantum mechanics. Entangled particles really are instantly connected, regardless of the distance between them. This doesn't violate special relativity, because no information can be transmitted faster than light. The correlations are perfect, but you can't control them to send messages. But some interpretations of quantum mechanics preserve locality by sacrificing realism. In these views, particles simply don't have definite properties until measured. The act of measurement doesn't reveal pre-existing properties, it participates in creating them. Reality is fundamentally participatory, with observers playing an active role in determining what exists. Some scientists speculate that this quantum correlation might be related to the structure of space-time itself.
Hall.
Perhaps the geometry of space and time emerges from patterns of quantum entanglement, with distance and duration being derived concepts rather than fundamental features of reality. Bell's theorem also reveals something profound about the nature of information and correlation. The universe seems to contain a deeper level of connection than classical physics allows. This connection isn't mediated by any known force or field. It's a fundamental feature of quantum reality. The implications extend beyond physics into philosophy and consciousness studies. If realism is false, if properties don't exist until measured, then what role does consciousness play in creating reality? Some interpretations suggest that conscious observation is what collapses quantum superposition states, making observers fundamental to the existence of definite properties. Recent experiments have closed various loopholes in Bell's theorem tests, making the conclusions increasingly secure. Scientists have performed Bell tests using particles separated by hundreds of kilometers, using random number generators to choose measurement settings, and even using cosmic photons from distant quasars to ensure the randomness of the measurements. Bell's theorem also challenges our understanding of causality and free will. If the universe is not locally realistic, then the classical notion of cause and effect becomes more complex. Events might be correlated not because one causes the other, but because they are part of a larger quantum system that transcends our usual understanding of space and time. As you prepare for sleep tonight, consider that your consciousness might be participating in the creation of reality through quantum measurement. Your thoughts, perceptions, and dreams might be collapsing quantum superposition states, selecting specific realities from the vast space of quantum possibilities. Each successful test confirms that our universe is stranger than we imagined. We live in a reality where distant events can be perfectly correlated, where particles can lack definite properties until measured, where the act of observation plays a fundamental role in determining what exists. The correlations revealed by Bell's theorem might extend to consciousness itself. Perhaps your mental states are entangled with the quantum processes in your brain, creating the unified experience of awareness from distributed neural activity. Your sense of self might emerge from quantum correlations that transcend the classical boundaries of space and time. In the quiet darkness of your bedroom, you are not just an observer of quantum reality, you are a participant in its creation. Every conscious moment, every act of perception, every dream that visits you in sleep participates in the eternal quantum dance that transforms possibility into actuality, that weaves the fabric of reality itself. The mysterious connections revealed by quantum entanglement are no longer just subjects of philosophical wonder. They're becoming the foundation for revolutionary new technologies. Scientists and engineers are learning to harness these spooky quantum correlations to create communication networks that would have seemed like pure magic just decades ago. Quantum communication begins with the strange property that quantum states are fundamentally fragile. Any attempt to eavesdrop on a quantum message necessarily disturbs the quantum state, revealing the presence of the intruder. This isn't a limitation of our technology, it's a fundamental feature of quantum mechanics. You cannot copy or perfectly measure a quantum state without changing it. This fragility, which might seem like a disadvantage, actually provides the foundation for absolutely secure communication. When two people share entangled particles, they can use the correlations between their particles to create encryption keys that are fundamentally impossible to hack. Any attempt to intercept the quantum key would immediately reveal itself through disturbances in the quantum correlations. The first quantum communication networks have already been built. In China, scientists have created a quantum communication network spanning thousands of kilometers, using both fiber optic cables and satellite links. Messages sent through this network are protected by the laws of quantum mechanics themselves, making them theoretically unhackable. These networks work by distributing entangled particles between different locations. When you want to send a secure message, you and your correspondent use your entangled particles to generate identical random keys. These keys are then used to encrypt and decrypt messages sent through conventional channels. Because the keys are generated by quantum correlations, any attempt to intercept them would be immediately detected. But quantum networks promise capabilities far beyond just secure communication. Scientists are developing quantum internet protocols that would allow quantum computers to be networked together, creating computational power that far exceeds what any single quantum computer could achieve alone. In a quantum internet, quantum computers wouldn't just exchange classical information, they would share quantum states directly. This would allow for distributed quantum computing, where complex problems could be solved by quantum processors working together across vast distances, their quantum states remaining entangled throughout the computation. The implications are staggering. Quantum networks could enable new forms of distributed quantum sensing, where sensors across the globe are quantum mechanically connected, allowing for unprecedented precision in measurements of gravitational waves, magnetic fields, and other subtle phenomena. The enhanced sensitivity would come from the quantum correlations between distant sensors, creating a global quantum sensing network. The challenges of building quantum networks are immense. Quantum states are incredibly fragile, easily destroyed by environmental interference. Creating stable quantum communication channels requires sophisticated error correction, quantum repeaters, to extend the range of quantum signals, and precise control over quantum states across vast distances. Scientists are developing quantum repeaters, devices that can extend the range of quantum communication by creating intermediate entangled states without destroying the quantum correlations. These repeaters use quantum error correction and quantum teleportation to maintain entanglement across distances much greater than would otherwise be possible. Quantum networks might also enable new forms of quantum artificial intelligence. If quantum computers can share quantum states directly, they could potentially share aspects of quantum consciousness or quantum cognition. Machine learning algorithms running on quantum networks might exhibit emergent behaviors that arise from the quantum entanglement between distributed processes. This process requires classical communication to complete the teleportation, so it doesn't violate the speed of light limit. But it does allow quantum information to be transmitted in a way that's impossible to intercept. because the quantum state is never actually traveling through the intermediate space. Quantum teleportation, despite its science fiction name, is a real phenomenon that allows quantum states to be transferred from one location to another using entangled particles. The original particle isn't physically moved. Instead, its quantum state is reconstructed at the destination using the correlations provided by entanglement. So, what are Nisand 1, Future quantum networks might enable quantum cloud computing, where users can access quantum computational resources distributed across the globe. Complex quantum algorithms could be executed on quantum processors located anywhere in the world, with the results delivered through quantum encrypted channels. The long-term vision is for a global quantum internet that seamlessly integrates quantum communication, computation, and sensing. This network would provide unprecedented security, computational power, and sensing capabilities, all based on the fundamental quantum correlations that connect particles across space and time. The boundaries between quantum networks and biological systems are also being explored. Some scientists speculate that biological systems might naturally form quantum networks, with quantum entanglement playing a role in processes like photosynthesis, bird navigation, and even consciousness itself. If consciousness involves quantum processes, then quantum networks might eventually interface directly with biological neural networks. This could enable new forms of brain-computer interfaces that operate at the quantum level, allowing direct quantum communication between minds and machines. As you drift towards sleep tonight, consider that you might already be part of a vast quantum network. The quantum fields that permeate your body are correlated with quantum processes throughout the universe. Your consciousness might be connected to the cosmic quantum network through the entangled particles in your brain, participating in the eternal exchange of quantum information that connects all things. The atoms in your body were forged in stellar furnaces billions of years ago, and they might still maintain quantum correlations with the cosmic processes that created them. In the deepest sense, you are not separate from the universe. You are a node in the cosmic quantum network, forever connected to the vast web of quantum correlations that underlies all of reality. In 1927, a young German physicist named Werner Heisenberg made a discovery that would fundamentally change our understanding of knowledge itself. Working late into the night in his laboratory, Heisenberg realized that the universe places absolute limits on what can be known. His uncertainty principle wasn't just a statement about the limitations of measurement, it was a profound insight into the nature of reality itself. The uncertainty principle states that certain pairs of properties cannot be simultaneously known with perfect precision. The most famous example involves position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't because our instruments aren't good enough, it's because the universe itself makes such complete knowledge impossible. To understand why this is so revolutionary, imagine trying to observe a particle. To see it, you need to bounce light off it, but light carries energy, and that energy disturbs the particle, changing its motion. The more precisely you want to know the particle's position, the more energetic the light you need to use, which disturbs the particle's motion even more. But Heisenberg's insight went deeper than just the practical problems of measurement. He realized that the uncertainty principle reflects something fundamental about the nature of reality itself. Particles don't have definite positions and moment simultaneously. These properties are complementary aspects of a deeper quantum reality that cannot be fully captured by classical concepts. This complementarity extends far beyond position and momentum. Energy and time form another complementary pair. You cannot simultaneously know the exact energy of a system and the exact time at which it has that energy. The angular momentum of a particle in different directions cannot be simultaneously determined. Even the number of particles in a quantum field and the phase of that field are complementary properties. The uncertainty principle reveals that the universe is not a collection of objects with definite properties, but rather a web of relationships and possibilities. Properties like position and momentum are not intrinsic features of particles. They emerge from the interaction between quantum systems and the act of measurement. This has profound implications for causality and determinism. In classical physics, if you know the position and momentum of every particle in the universe, you can predict the future with perfect accuracy. But the uncertainty principle makes this impossible even in principle. The universe retains an element of fundamental unpredictability, not because of our ignorance, but because of the nature of quantum reality itself. Heisenberg's insight also reveals the participatory nature of reality. The act of measurement doesn't just reveal pre-existing properties, it participates in creating them. When you measure a particle's position, you're not just discovering where it is, you're participating in the process that gives it a definite position. The uncertainty principle also governs the relationship between different aspects of quantum systems. The more precisely a quantum system is prepared in one state, the more uncertain it becomes in complementary states. This creates a fundamental trade-off in how quantum systems can be prepared and measured. This trade-off has practical implications for quantum technologies. Quantum computers exploit uncertainty by preparing quantum bits in superposition states, where their values are maximally uncertain. This uncertainty is what allows quantum computers to explore multiple computational paths simultaneously, potentially solving problems that would be impossible for classical computers. The uncertainty principle also explains why atoms are stable. If electrons could have definite positions and moment simultaneously, they would spiral into the nucleus and atoms would collapse. The uncertainty principle provides the quantum pressure that keeps electrons in stable orbitals, making chemistry and life possible. These virtual particles aren't just theoretical constructs, they have measurable effects. They influence the energy levels of atoms, create forces between objects in the quantum vacuum, and even affect the behavior of light itself. The uncertainty principle makes the vacuum a bubbling sea of virtual activity. In quantum field theory, the uncertainty principle manifests as virtual particles that pop in and out of existence in the quantum vacuum. The uncertainty in energy allows the vacuum to borrow energy to create particle-antiparticle pairs, as long as they annihilate each other quickly enough that the energy debt is repaid within the time limit set by the uncertainty principle. This connection between uncertainty and information has led to insights about the nature of consciousness and observation. Some scientists speculate that consciousness itself might be understood as a quantum information processing system, with the uncertainty principle governing the trade-offs between different aspects of conscious experience. The principle also reveals the deep connection between quantum mechanics and information theory. The uncertainty principle can be understood as a statement about the information content of quantum states. A quantum system can only contain a finite amount of information about its various properties, and measuring one property necessarily destroys information about complementary properties. As you prepare for sleep tonight, consider that your consciousness might be governed by its own uncertainty principles. The more precisely you try to focus on one thought, the more uncertain other aspects of your mental state become. The flow of consciousness might be a manifestation of quantum uncertainty in the neural networks of your brain. The act of measurement, something we take for granted in our everyday lives, becomes profoundly mysterious when we venture into the quantum realm. Here, the simple act of observation doesn't just reveal reality, it participates in creating it. The relationship between measurement and reality in quantum mechanics challenges our most basic assumptions about the nature of existence itself. The uncertainty principle suggests that perfect knowledge is not just practically impossible, it's fundamentally meaningless. The universe reserves the right to remain mysterious, to maintain pockets of fundamental unpredictability that ensure the future remains open and creative. In the quiet darkness of your bedroom, you are surrounded by quantum uncertainty. Every particle in your body exists in a state of fundamental uncertainty, dancing on the edge between definite and indefinite, between known and unknowable, between what is and what might be. But quantum mechanics reveals a startling truth. At the fundamental level, measurement is active. When you measure a quantum system, you're not just discovering its properties, you're participating in the process that gives it those properties. The measurement doesn't reveal what was already there, it helps determine what comes to exist. In the classical world, Measurement is passive. When you measure the temperature of your room, you're discovering something that already exists. The thermometer reveals the temperature, but doesn't create it. The room has a definite temperature, whether or not you measure it. This seems obvious, natural, the way things should be. This is because quantum systems exist in superposition states before measurement. An electron doesn't have a definite position until you measure it. It exists as a probability cloud, simultaneously present in multiple locations. The act of position measurement forces the electron to choose a specific location from all its possible locations. But here's the mysterious part. The choice isn't predetermined. The electron doesn't know where it will be found when you measure it. The measurement interaction somehow selects one outcome from the quantum possibilities, but the selection process itself seems to involve an element of fundamental randomness. This randomness isn't due to our ignorance or the limitations of our instruments. It's built into the fabric of reality itself. Even with perfect knowledge of a quantum system's wave function, you can only predict probabilities of measurement outcomes, never the specific result of any individual measurement. The measurement process involves what physicists call wave function collapse. Before measurement, the quantum system exists in a superposition of all possible states. The measurement interaction causes this superposition to collapse into a single definite state. But what causes this collapse? What determines which of the many possible outcomes actually occurs? But regardless of the interpretation, all agree that measurement plays a fundamental role in quantum mechanics. The universe seems to distinguish between measured and unmeasured systems, between observed and unobserved properties, between potential and actual states. This is one of the deepest mysteries in physics, known as the measurement problem. Different interpretations of quantum mechanics provide different answers. The Copenhagen interpretation suggests that measurement by a classical apparatus causes collapse. The many worlds interpretation proposes that all outcomes occur, but in parallel universes. The consciousness-based interpretation suggests that conscious observation is what causes collapse. This leads to a profound philosophical question. Does reality exist independent of observation? In classical physics, the answer is clearly yes. But quantum mechanics suggests that reality might be fundamentally observer-dependent. Properties might not exist until measured. States might not be definite until observed. Events might not be actual until recorded. The measurement process also reveals the crucial role of information in quantum mechanics. Whole measurement is fundamentally about gaining information about a quantum system. But in quantum mechanics, information is not passive. It's an active participant in the creation of reality. This creates a fundamental trade-off. Gaining information about one aspect of a quantum system necessarily destroys information about other aspects. The uncertainty principle can be understood as a statement about this information trade-off. Measurement doesn't just reveal information, it actively redistributes it. When you measure a quantum system, you're establishing a correlation between the system and the measuring device. This correlation allows information about the system to be recorded and preserved. But the process of creating this correlation necessarily disturbs the quantum system, changing its state in unpredictable ways. The relationship between measurement and reality also has profound implications for the nature of time. In classical physics, the past is fixed and the future is open. But in quantum mechanics, the future might influence the past through the measurement process. Some interpretations suggest that measurement events can retroactively determine the history of quantum systems. The measurement process also reveals the participatory nature of reality. Observers aren't separate from the systems they observe. They're part of a larger quantum system that includes both the observer and the observed. The act of observation creates entanglement between the observer and the observed, making them parts of a single quantum system. This temporal non-locality means that reality might not unfold in a simple linear fashion from past to future. Instead, the measurement process might create a more complex web of causal relationships where future measurements influence past states and past preparations influence future measurements. This participatory universe means that consciousness might play a fundamental role in the creation of reality, Some scientists speculate that conscious observation is what causes wave function collapse, making conscious beings active participants in the unfolding of reality. As you drift towards sleep tonight, consider that your consciousness might be continuously measuring and collapsing quantum states in your brain. Your thoughts, perceptions, and dreams might be the result of quantum measurements that select specific neural configurations from the vast space of quantum possibilities. The boundary between sleeping and waking might be understood as different modes of quantum measurement. Or during waking consciousness, rapid measurements create the stable, classical-like experience of everyday reality. During sleep, slower or different measurement processes might allow for the fluid, superposition-rich experience of dreams. In the quiet darkness of your bedroom, your consciousness is engaged in the eternal dance of measurement and reality creation. Every moment of awareness, every fleeting thought, every dream that visits you participates in the ongoing quantum measurement that transforms possibility into actuality, that weaves the fabric of reality itself. The uncertainty principle doesn't just place limits on what we can know, it fundamentally challenges our understanding of causality and determinism. In a universe where the future cannot be predicted with perfect accuracy, where measurement participates in creating reality, and where quantum events contain irreducible elements of randomness, the relationship between cause and effect becomes far more subtle and mysterious than we ever imagined. Classical physics painted a picture of a deterministic universe. If you knew the position and momentum of every particle in the universe, you could, in principle, predict the future with perfect accuracy. The universe was like a vast clockwork mechanism, with every event following inevitably from the events that preceded it. This was the worldview that dominated science for centuries. But the uncertainty principle destroys this deterministic vision. If you cannot simultaneously know the position and momentum of even a single particle with perfect precision, then perfect prediction becomes impossible, not just in practice, but in principle. The universe retains an element of fundamental unpredictability that cannot be eliminated by better measurements or more sophisticated theories. This doesn't mean that the universe is completely random. Quantum mechanics provides precise predictions for the probabilities of different outcomes. The uncertainty principle governs how these probabilities evolve over time, creating a new kind of causality based on probability rather than certainty. In this probabilistic causality, causes don't determine effects. They influence the probabilities of different effects. When you set up a quantum experiment, you're not determining what will happen. You're shaping the probability landscape of what might happen. The actual outcome emerges from the quantum measurement process in a way that cannot be predicted with certainty. This has profound implications for our understanding of free will. If the universe is fundamentally deterministic, then free will becomes problematic. Our choices would be the inevitable result of prior causes. But if the universe contains genuine quantum randomness, then our choices might not be completely determined by the past. Some scientists speculate that consciousness might exploit quantum uncertainty to create genuine free will. The quantum processes in our brains might amplify quantum uncertainties into macroscopic choices, allowing our decisions to be influenced by quantum events that are not completely determined by prior causes. The uncertainty principle also challenges our understanding of causality in more subtle ways. In quantum mechanics, the order of measurements can affect the outcomes, even when the measurements are performed on the same system. This suggests that causality might be more context-dependent than we assumed. This non-commutative nature of quantum measurements suggests that causality itself might be fundamentally quantum mechanical. The classical notion of a linear chain of cause and effect might be a simplified approximation that breaks down when we look closely at the quantum level. The uncertainty principle also creates what physicists call quantum indeterminacy. Even with perfect knowledge of a quantum system's initial state, the outcomes of measurements remain fundamentally unpredictable. This indeterminacy isn't due to ignorance, it's a feature of reality itself. Consider two measurements performed on the same quantum system. If you measure property A first and then property B, you might get different results than if you measure property B first and then property A. The order of causation matters in quantum mechanics in ways that have no classical analog. This quantum indeterminacy might be what allows for genuine novelty and creativity in the universe. If everything were completely determined by prior causes, then the universe would be static and unchanging at the deepest level. But quantum uncertainty creates space for genuine novelty, for outcomes that are not completely determined by the past. The relationship between uncertainty and time also challenges our understanding of causality. In quantum mechanics, events that are separated by very small time intervals can be causally connected in ways that violate our classical intuitions. The uncertainty principle allows for virtual particles to exist for brief periods, creating causal connections that wouldn't be possible in classical physics. These virtual processes suggest that causality might be more flexible than we assumed. Events might be connected by quantum fluctuations that exist for times so brief that they cannot be directly observed, creating a hidden network of causal relationships that underlies the apparent stability of the macroscopic world. The uncertainty principle also implies that the future might influence the past in subtle ways. Some interpretations of quantum mechanics suggest that measurement events can retroactively determine the history of quantum systems. This creates a kind of temporal non-locality, where the arrow of time becomes more complex than simple linear progression from past to future. This temporal aspect of quantum mechanics suggests that causality might be more like a web than a chain. Past, present, and future might be interconnected in ways that create complex patterns of influence that cannot be reduced to simple cause and effect relationships. As you prepare for sleep tonight, consider that your consciousness might be navigating a landscape of quantum causality. Your thoughts, decisions, and dreams might be influenced by quantum processes that are not completely determined by your past experiences. Imagine walking toward a brick wall, and instead of stopping, you simply pass through it as if it weren't there. This sounds like pure fantasy, the stuff of ghost stories and science fiction. Yet in the quantum world, particles routinely perform this impossible feat. They pass through barriers that should completely stop them, emerging on the other side as if by magic. This phenomenon, known as quantum tunneling, is one of the most remarkable and counterintuitive aspects of quantum mechanics. The uncertainty principle suggests that your future is not completely determined by your past. There remain pockets of genuine openness, spaces where quantum uncertainty allows for genuine choice and creativity. Your dreams tonight might explore some of these quantum possibilities, visiting potential futures that are not completely determined by your present circumstances. Yen, in the quiet darkness of your bedroom, you exist at the intersection of determinism and freedom, of causality and creativity, of the determined and the open. The uncertainty principle ensures that your future remains partly unwritten, partly open to the creative possibilities that emerge from the quantum heart of reality itself. But quantum particles are described by wave functions, probability waves that extend throughout space. These waves don't have sharp boundaries like classical objects. Instead, they fade gradually as they encounter barriers. Even when the particle doesn't have enough energy to classically overcome a barrier, its wave function can extend beyond the barrier, creating a small but non-zero probability that the particle will be found on the other side. To understand quantum tunneling, we must first understand how quantum particles differ from classical objects. When you throw a ball at a wall, it either has enough energy to go over the wall, or it doesn't. If it doesn't have enough energy, it bounces back. The wall presents a definite barrier that the ball cannot cross, unless it has sufficient energy to overcome it. This is the essence of quantum tunneling. The particle's wave function partially penetrates the barrier, and there's a quantum probability that the particle will appear on the other side, even though it doesn't have enough energy to go over or around the barrier. The particle doesn't physically travel through the barrier. It somehow materializes on the other side. The probability of tunneling depends on several factors: the width of the barrier, its height, and the mass of the particle. Thinner barriers are easier to tunnel through. Lower barriers present less of an obstacle. Lighter particles tunnel more easily than heavier ones, but even under the best conditions, Tunneling probabilities are usually very small for macroscopic objects. This is why you can't walk through walls. Your body is made of particles that are far too massive, and walls are far too thick and tall, in quantum terms, for any significant tunneling probability. The chance of all the particles in your body tunneling through a wall simultaneously is so incredibly small that it would never happen in the lifetime of the universe. But for individual subatomic particles, tunneling is a routine occurrence. Electrons tunnel through barriers in electronic devices every day. Alpha particles tunnel out of atomic nuclei during radioactive decay. Even protons can tunnel through energy barriers under the right conditions. End of the system versus wah, the wah. The mathematics of quantum tunneling reveals something profound about the nature of reality. The tunneling probability depends on the exponential of the barrier's properties, meaning that small changes in the barrier can create dramatic changes in the tunneling rate. This exponential sensitivity makes tunneling a remarkably precise phenomenon despite its probabilistic nature. Quantum tunneling also challenges our understanding of energy conservation. Or classically, a particle cannot pass through a barrier taller than its energy, but in quantum mechanics, particles can borrow energy from the quantum vacuum to tunnel through barriers, as long as they repay this energy quickly enough to satisfy the uncertainty principle. This energy borrowing isn't just a theoretical curiosity. It has measurable effects. The tunneling process can be instantaneous, with particles appearing on the other side of barriers without spending any time traveling through them. This raises profound questions about the speed of quantum tunneling and its relationship to the speed of light. Some experiments suggest that quantum tunneling might be faster than light, at least in the sense that the time spent tunneling through a barrier can be zero or even negative. This doesn't violate relativity because no information can be transmitted faster than light using tunneling, but it does suggest that the quantum realm operates according to different rules than classical physics. The phenomenon of tunneling also reveals the probabilistic nature of quantum reality. Even with identical particles approaching identical barriers, some will tunnel through, while others will not. The outcome for any individual particle cannot be predicted. Only the statistical distribution of outcomes can be calculated. This randomness is not due to our ignorance or the limitations of our measuring instruments. It's a fundamental feature of quantum mechanics. The universe makes random choices about which particles tunnel and which don't, and these choices cannot be predicted in advance. The implications of quantum tunneling extend beyond physics into philosophy and consciousness studies. If consciousness involves quantum processes, then perhaps thoughts and ideas can tunnel through conceptual barriers in ways that defy classical logic. Creative insights might emerge from quantum tunneling processes in the brain, allowing new ideas to appear suddenly without following the usual step-by-step reasoning. Quantum tunneling also demonstrates the non-local nature of quantum mechanics. The tunneling probability depends on the global properties of the barrier, not just the local conditions where the particle encounters it. A change in the barrier's properties, far from the particle's location, can instantly affect the tunneling probability. As you drift towards sleep tonight, consider that your consciousness might be capable of its own form of quantum tunneling. Your dreams might allow you to pass through the barriers of everyday logic and causality, exploring impossible landscapes and experiencing events that would be forbidden in the waking world. Every morning, sunlight streams through your window, warming your face and illuminating the world around you. That light carries energy that traveled 93 million miles from the sun's core, where it was created by one of the most remarkable applications of quantum tunneling in the universe. Without quantum tunneling, the sun would never have ignited, stars would never have formed, and life as we know it would be impossible. In the quiet darkness of your bedroom, quantum tunneling is happening all around you. Particles in the walls, in the air, in your own body are constantly tunneling through barriers, creating the subtle quantum processes that underlie the stability of matter and the flow of energy through the universe. The boundary between sleeping and waking might itself be a kind of quantum barrier that consciousness can tunnel through. In dreams, you might experience quantum tunneling directly, moving through walls, traveling instantly across vast distances, and experiencing the fluid, probabilistic nature of quantum reality. The heart of the sun is a furnace of unimaginable intensity, where temperatures reach 15 million degrees Celsius and pressures are 200 billion times greater than at Earth's surface. Even under these extreme conditions, something seemingly impossible must happen for the sun to shine. Hydrogen nuclei must overcome their mutual electrical repulsion and get close enough to fuse together. Here's the remarkable thing. Even at the sun's core temperature, hydrogen nuclei don't have enough energy to classically overcome the Coulomb barrier. If classical physics were the whole story, nuclear fusion would be impossible. The sun would be cold and dark, and none of us would exist. Hydrogen nuclei are positively charged protons, and like charges repel each other. This electrical repulsion creates what physicists call the Coulomb barrier, an energy barrier that prevents nuclei from approaching each other. For nuclei to fuse, they must overcome this barrier and get close enough for the strong nuclear force to bind them together. With so many protons and so many collisions, even the tiny tunneling probability becomes significant. Roughly 600 million tons of hydrogen are converted to helium in the sun's core every second through quantum tunneling. This process releases the energy that makes the sun shine and makes life on Earth possible. But quantum mechanics provides a solution through tunneling. Even though individual protons don't have enough energy to go over the Coulomb barrier, their quantum wave functions can penetrate through it. There's a small but crucial probability that protons will tunnel through the barrier and fuse together, releasing energy in the process. This tunneling probability is incredibly small for any individual pair of protons. The chance that two specific protons will tunnel through the barrier and fuse is almost negligible. But the sun's core contains an enormous number of protons, about 10 circumflex 57 of them, and they're constantly colliding with each other billions of times per second. The sensitivity of tunneling to small changes in conditions means that stellar fusion is remarkably fine-tuned. If the fundamental constants of physics were slightly different, if the strong nuclear force were a bit weaker, or the electromagnetic force a bit stronger, quantum tunneling would be too improbable for stars to shine. The universe would be cold, dark, and lifeless. This fine-tuning extends to the formation of heavier elements necessary for life. Carbon, oxygen, nitrogen, and other elements essential for biology are created in the cores of massive stars through fusion processes that also depend on quantum tunneling. When these stars explode as supernovae, they scatter these elements throughout the universe, providing the raw materials for planets and life. The quantum tunneling that powers stars also operates in more subtle ways throughout the universe. In the cores of planets, radioactive decay processes that depend on quantum tunneling generate the heat that drives geological activity. On Earth, this geothermal energy powers plate tectonics, which helps regulate the planet's climate and creates the geological diversity that supports life. The hydrogen bonds that hold DNA's double helix together can undergo quantum tunneling, allowing protons to switch positions in ways that might contribute to genetic mutations. This quantum tunneling in DNA might be one of the mechanisms that drives evolution, creating the genetic diversity that allows life to adapt and evolve. Even photosynthesis, the process that converts sunlight into chemical energy and produces the oxygen we breathe, depends on quantum tunneling. The initial steps of photosynthesis involve electrons tunneling through protein structures with remarkable efficiency, enabling plants to capture and convert solar energy. Quantum tunneling also plays crucial roles in biological systems. Many enzyme reactions that are essential for life depend on quantum tunneling to proceed at reasonable rates. The enzyme reactions that break down food in your cells, that repair DNA damage, and that synthesize important molecules all exploit quantum tunneling to overcome energy barriers that would otherwise make these reactions impossibly slow. Recent research suggests that quantum tunneling might also play a role in consciousness itself. Some scientists propose that quantum tunneling in microtubules within neurons could be part of the quantum processes that give rise to conscious experience. If this is true, then the same quantum phenomenon that powers the sun might also power your thoughts and dreams. As you drift towards sleep tonight, Consider that your existence depends on quantum tunneling events that occurred billions of years ago in the cores of ancient stars. The atoms in your body were forged by quantum tunneling processes that converted hydrogen into heavier elements, creating the carbon, oxygen, and nitrogen that make up your cells. The fragrance of flowers, the taste of food, and even your sense of smell might depend on quantum tunneling. Some theories suggest that our ability to distinguish between different odor molecules depends on quantum tunneling processes in our olfactory receptors, allowing us to detect subtle differences in molecular structure. The warmth of your bed, the oxygen in your lungs, the beating of your heart, all of these depend on the quantum tunneling that powers the sun and creates the energy that sustains life on Earth. You are not separate from the quantum processes that power the universe. You are the universe becoming aware of itself through the miracle of quantum tunneling. The quantum tunneling that powers the sun and enables life has quietly revolutionized the modern world. The device you're listening to this on, the lights in your room, the memory in your computer, even the GPS satellites that guide your navigation, all of these depend on quantum tunneling. This seemingly esoteric quantum phenomenon has become one of the most practical and widely used effects in modern technology. In the quiet darkness of your bedroom, quantum tunneling continues its invisible work, powering the cellular processes that maintain your life, enabling the chemical reactions that sustain your body, and perhaps even contributing to the dreams that will visit you in sleep. The electronic revolution began with the understanding of quantum tunneling in semiconductors. In the early days of electronics, vacuum tubes controlled the flow of electricity through empty space. But the invention of the transistor in 1947 marked the beginning of the solid-state revolution, and quantum tunneling played a crucial role in making transistors possible. In modern computer processors, transistors are now so small that quantum tunneling dominates their behavior. The gate oxide layers in these transistors are only a few atomic layers thick, allowing electrons to tunnel through them in controlled ways. In modern computer processors, transistors are now so small that quantum tunneling dominates their behavior. This quantum tunneling is both an opportunity and a challenge. It enables very small transistors to work, but it also creates power consumption and reliability challenges that engineers must carefully manage. Transistors work by controlling the flow of electrons through semiconductor materials. The barriers between different regions of a transistor can be precisely engineered to allow or prevent electron tunneling, creating the on-off switching behavior that forms the basis of all digital electronics. As transistors have become smaller and smaller, quantum tunneling has become increasingly important to their operation. Quantum tunneling has also enabled the development of scanning tunneling microscopes, STMs, which can image individual atoms on surfaces. These remarkable instruments work by bringing a sharp metallic tip very close to a surface, so close that electrons can tunnel between the tip and the surface. By monitoring the tunneling current as the tip scans across the surface, scientists can create images with atomic resolution. The flash memory in your smartphone, tablet, and computer depends entirely on quantum tunneling. These devices store information by trapping electrons in tiny wells surrounded by insulating barriers. Writing information requires electrons to tunnel through these barriers to enter the wells. Reading information involves detecting whether electrons are present in the wells. Erasing information requires electrons to tunnel back out of the wells. Each time you save a photo, send a text message, or install an app, you're using quantum tunneling to manipulate electrons in ways that store and retrieve information. The billions of memory cells in your devices are all quantum tunneling devices, each one capable of trapping and releasing electrons through quantum mechanical processes. STMs have revolutionized our understanding of surfaces and nanostructures. They've allowed scientists to manipulate individual atoms, to study chemical reactions at the atomic level, and to create nanostructures with unprecedented precision. The famous images of atoms arranged to spell out company logos or form molecular structures are all created using quantum tunneling. The precision of atomic clocks, which are essential for GPS navigation and many other modern technologies, also depends on quantum tunneling. These clocks work by monitoring the quantum transitions of atoms, and the accuracy of these transitions depends on quantum tunneling processes that occur within the atoms themselves. Quantum tunneling is also crucial for many types of sensors. Tunnel junction sensors can detect incredibly small magnetic fields, electrical currents, and even individual photons. These sensors exploit the extreme sensitivity of tunneling currents to small changes in barrier properties, achieving levels of precision that would be impossible with classical sensors. In the field of quantum computing, quantum tunneling is being used to create qubits, the basic building blocks of quantum computers. Superconducting qubits, one of the most promising approaches to quantum computing, work by allowing electric current to tunnel through Josephson junctions in superconducting circuits. These quantum tunneling events can be controlled and manipulated to perform quantum computations. Quantum tunneling is also being explored for energy applications. Tunnel diodes can convert heat directly into electricity through quantum tunneling processes, potentially creating more efficient solar cells and waste heat recovery systems. Researchers are also investigating quantum tunneling effects in fuel cells and batteries, where tunneling might enable more efficient energy storage and conversion. The emerging field of molecular electronics depends heavily on quantum tunneling. Researchers are developing electronic devices based on single molecules, where electrons tunnel through molecular structures to create transistors, memory devices, and sensors that are only a few atoms in size. These molecular devices could lead to electronics that are orders of magnitude smaller and more efficient than current silicon-based technology. The field of quantum cryptography depends on quantum tunneling for secure communication. Quantum key distribution systems use the quantum properties of photons, including their ability to tunnel through barriers, to create communication channels that are theoretically impossible to hack. These systems are already being deployed for secure communications in banking, government, and military applications. As you settle into sleep tonight, consider that your bedroom is filled with quantum tunneling devices. The LED lights that illuminate your room, the smartphone charging beside your bed, the smart home devices that control your environment. All of these depend on quantum tunneling to function. The boundary between the quantum world and the everyday world is not as clear as it once seemed. Quantum tunneling has brought the strange probabilistic nature of quantum mechanics into our daily lives, making the impossible possible and the improbable practical. In the quiet darkness of your bedroom, billions of quantum tunneling events are occurring every second in the electronic devices around you. Electrons are tunneling through barriers in your phone's memory, creating and preserving the digital traces of your life. The same quantum phenomenon that powers the sun is also powering the modern world, connecting the cosmic and the mundane in ways that would have seemed like magic just a few decades ago. In the 1920s, in the beautiful city of Copenhagen, a group of brilliant physicists gathered around Niels Bohr to wrestle with the profound mysteries of quantum mechanics. Their discussions, debates, and insights would give birth to what became known as the Copenhagen interpretation, the first systematic attempt to understand what quantum mechanics actually means for the nature of reality. The Copenhagen interpretation emerged from a simple yet radical idea. Quantum mechanics doesn't describe what reality is, but rather what we can know about reality through measurement. This subtle shift in perspective changes everything. Instead of asking, what is the electron doing? The Copenhagen interpretation asks, what can we observe about the electron when we measure it? This collapse isn't gradual or continuous. It's instantaneous and discontinuous. What physicists call a quantum jump. One moment, the electron is everywhere and nowhere. The next moment, it's here, specifically here, with a definite position and momentum. The measurement doesn't reveal where the electron was. It determines where the electron is. But what constitutes a measurement? This question has puzzled physicists for nearly a century. The Copenhagen interpretation suggests that measurement occurs when a quantum system interacts with a classical measuring apparatus. The apparatus must be classical in the sense that it has definite properties and can record specific outcomes. According to this interpretation, Quantum systems exist in superposition states until the moment of measurement. Before you observe an electron, it doesn't have a definite position. It exists as a probability cloud spread throughout space. The act of measurement causes what Bohr called complementarity. The wave function collapses, and the electron suddenly has a definite position. This leads to one of the most profound implications of the Copenhagen interpretation. It's the participatory nature of reality. Reality isn't independent of observation. It's created through the interaction between quantum systems and classical observers. The universe doesn't have definite properties until someone or something observes it. This creates a curious division of the world into quantum and classical realms. Quantum systems obey the strange rules of superposition and entanglement, while classical systems have definite properties and follow deterministic laws. The boundary between these realms is drawn wherever measurement occurs. The role of the observer becomes crucial in this interpretation. The observer doesn't have to be conscious. A photographic plate can serve as an observer, as can a computer or any device capable of recording information. But the observer must be classical, must have definite properties, and must be able to record specific outcomes. The Copenhagen interpretation also embraces the concept of complementarity as a fundamental feature of reality. Wave and particle descriptions of matter are complementary, both are true, but they cannot be observed simultaneously. You can measure the wave-like properties of an electron or its particle-like properties, but never both at the same time. The interpretation also grapples with the problem of quantum randomness. When a quantum measurement is performed, the outcome is genuinely random, not predictable, even in principle. This randomness isn't due to our ignorance or the limitations of our theories. It's a fundamental feature of reality itself. This complementarity extends beyond physics into the nature of knowledge itself. According to Bohr, complementarity might be a general feature of complex systems. Perhaps consciousness itself involves complementary aspects that cannot be simultaneously observed. Aspects like reason and emotion, individual and collective experience, or subjective and objective reality. This quantum randomness challenged Einstein deeply. His famous objection, "God does not play dice with the universe," was directed at this aspect of the Copenhagen interpretation. Einstein believed that quantum mechanics must be incomplete, that there must be hidden variables that determine the outcomes of quantum measurements. The interpretation also addresses the measurement problem through what's called the von Neumann cut, an arbitrary boundary between the quantum system being observed and the classical apparatus doing the observing. This boundary can be moved, but it must exist somewhere to make sense of quantum mechanics. But the Copenhagen interpretation embraces this randomness as fundamental. The universe does play dice, and these dice are perfectly random. The future is not completely determined by the past. Quantum measurements introduce genuine novelty into the universe. Critics of the Copenhagen interpretation point out that it seems to require a fundamental division between quantum and classical realms, but it doesn't explain where this division comes from or why it exists. If everything is ultimately made of quantum particles, why do some systems behave classically while others behave quantum mechanically? The interpretation also raises questions about the nature of reality before observation. If properties don't exist until measured, what is the status of the universe before conscious observers evolved? Did the universe exist in a superposition state for billions of years before life appeared to observe it? The super-C. Despite these challenges, the Copenhagen interpretation remains influential because it provides a practical framework for understanding quantum mechanics. It tells us how to calculate probabilities, how to understand measurements, and how to think about the relationship between quantum theory and experimental observations. The Copenhagen interpretation suggests that your consciousness is not separate from the physical world. It's an integral part of the quantum measurement process that creates definite reality from quantum possibilities. Your awareness might be one of the mechanisms through which the universe observes itself and collapses into definite states. As you drift towards sleep tonight, consider that your consciousness might be playing the role of a quantum observer. Your thoughts, perceptions, and dreams might be collapsing quantum superposition states in your brain. selecting specific neural configurations from the vast space of quantum possibilities. In the quiet darkness of your bedroom, you exist at the boundary between quantum and classical realms, between possibility and actuality, between the observed and the observer. Your consciousness participates in the eternal dance of quantum measurement that transforms the potential into the actual, the probable into the definite. What if every time you make a decision, the universe splits? What if every quantum measurement creates not one outcome, but all possible outcomes, each occurring in its own parallel reality? This is the breathtaking vision of the many worlds interpretation of quantum mechanics, proposed by Hugh Everett III in 1957. It's a theory so radical that it suggests our entire universe is just one branch of an infinite tree of parallel realities. The many worlds interpretation begins with a simple but profound insight. What if quantum wave functions never collapse? What if quantum wave functions never collapse? What if the superposition states we've been discussing don't disappear during measurement, but instead continue to exist in parallel universes? Instead of the quantum world giving way to classical reality, perhaps all quantum possibilities are equally real, each unfolding in its own branch of the multiverse. Imagine Schrödinger's cat experiment through the lens of many worlds. When the quantum event occurs, the universe splits into two branches. In one branch, the cat lives. In another branch, the cat dies. Both outcomes are equally real, equally actual, but they exist in parallel universes that cannot communicate with each other. You, as the observer, also split. There's a version of you in the universe where you open the box and find a living cat, and another version of you in the universe where you discover a dead cat. Both versions are real. Both have conscious experiences, but they exist in different branches of the multiverse and can never compare notes. This splitting happens not just for dramatic quantum events, but for every quantum measurement, every quantum interaction, every moment when quantum possibilities could go one way or another. The universe is constantly branching, creating new parallel realities at an astronomical rate. The many worlds interpretation solves several problems that plague other interpretations of quantum mechanics. It eliminates the need for wave function collapse, avoiding the mysterious process by which quantum superposition supposedly gives way to classical reality. It preserves the deterministic evolution of the wave function. Nothing random happens to the wave function itself, only to which branch of reality we find ourselves experiencing. It also resolves the measurement problem by eliminating the need for a special measurement process. Every interaction between quantum systems causes the universe to branch, with each branch corresponding to a different outcome of the interaction. There's no need for classical measuring devices or conscious observers. The branching happens automatically whenever quantum systems interact. Hall. In the many worlds interpretation, the apparent randomness of quantum mechanics is explained as ignorance about which branch of the multiverse we're in. When you perform a quantum measurement, you're not creating a random outcome. You're discovering which branch of the multiverse you happen to inhabit. The randomness is epistemic, related to knowledge, rather than ontological, related to reality itself. This interpretation has profound implications for the nature of probability and prediction. When quantum mechanics predicts that an event has a 50% probability of occurring, it doesn't mean the event might or might not happen. It means that in 50% of the branches of the multiverse, the event occurs, and in 50% of the branches, it doesn't occur. The interpretation also suggests that every possible history of the universe actually occurs somewhere in the multiverse. There are branches where the dinosaurs never went extinct, where you became a famous musician, where technological development took completely different paths. Symboltinso because also of contentidia the hawazidi suri y symbolsia devel. Every story that could be told is being told somewhere in the vast library of parallel worlds. Defies might be so. Some philosophers argue that the many worlds interpretation actually supports a kind of immortality. If you're constantly splitting into different versions, and some versions of you might avoid death in each situation, then perhaps there's always a branch of the multiverse where you survive. This leads to the speculation about quantum immortality. the idea that consciousness might always experience the branch where it continues to exist. The many worlds interpretation also raises fascinating questions about identity and consciousness. If you're constantly splitting into multiple versions of yourself, which version is the real you? Are all versions equally real? Do they all have equally valid conscious experiences? The interpretation also has implications for the nature of time and causality. If all possible futures exist in parallel branches, then perhaps the future is not open, but already determined in the sense that all possibilities are actualized. Time might be more like a branching tree than a single timeline. This raises questions about the nature of moral responsibility and meaning. If every possible choice occurs in some branch of the multiverse, do your choices matter? Some argue that they matter deeply because they determine which branch of the multiverse you experience. Others suggest that the many worlds interpretation undermines the significance of individual choices. Critics of the many worlds interpretation point out that it seems to require an enormous, even infinite, number of parallel universes. They question whether such a vast ontology is justified, especially when these other universes can never be observed or tested. The interpretation is also criticized for its apparent untestability. If we can never observe other branches of the multiverse, how can we know they exist? As you drift towards sleep tonight, consider that there might be countless versions of you across the multiverse, each experiencing slightly different versions of this moment. In some branches, you're already asleep. In others, you're reading something completely different. In still others, you're living entirely different lives. The many worlds interpretation suggests that your dreams might be glimpses of parallel realities, windows into other branches of the multiverse, where different versions of you are experiencing different possibilities. Perhaps sleep is when consciousness becomes less tightly bound to a single branch of reality, allowing you to experience the quantum superposition of multiple worlds. In the quiet darkness of your bedroom, the universe might be constantly branching around you, creating new realities with each quantum event. You are not just living one life, you are living all possible lives, experiencing all possible futures, exploring all possible versions of yourself across the infinite expanse of the multiverse. The pilot wave theory, originally proposed by Louis de Broglie and later developed by David Bohm, suggests that particles have definite positions and velocities at all times, but they're guided by a quantum wave that pervades all of space. This pilot wave is real but non-material, influencing the motion of particles without being influenced by them. The theory preserves determinism while explaining quantum phenomena through the action of this invisible guiding field. Beyond the Copenhagen interpretation and many worlds theory, quantum mechanics has spawned a rich garden of interpretations, each offering a different vision of reality's fundamental nature. These interpretations aren't just academic exercises. They represent profoundly different ways of understanding what it means to exist, to observe, and to be conscious in a quantum universe. In this interpretation, quantum uncertainty arises not from the fundamental nature of reality, but from our ignorance of the initial conditions and the detailed workings of the pilot wave. The universe is deterministic, but the pilot wave is so sensitive to initial conditions that it appears random to us. This theory suggests that reality is far richer than we can directly observe, containing hidden variables that determine the outcomes of quantum measurements. This interpretation explains why macroscopic objects don't exhibit quantum superposition. They're constantly undergoing spontaneous collapses that maintain their classical behavior. The theory suggests that reality is fundamentally stochastic, with genuine randomness built into the fabric of space-time itself. The spontaneous collapse theory, developed by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber, proposes that wave functions actually do collapse spontaneously, without the need for measurement or observation. In this view, particles occasionally undergo random spontaneous collapses that localize them in space. These collapses are extremely rare for individual particles, but become more frequent as systems become larger and more complex. The consciousness-based interpretations, explored by physicists like Eugene Wigner and later developed by others, propose that consciousness plays a fundamental role in quantum mechanics. In these interpretations, wave function collapse is triggered by conscious observation. The universe exists in superposition until a conscious mind observes it, at which point reality crystallizes into a definite state. This interpretation suggests that reality is fundamentally relational rather than absolute. There's no view from nowhere. All properties and events exist only in relation to specific observers or systems. The universe is not a collection of objects with definite properties, but a web of relationships and interactions. The relational interpretation, developed by Carlo Rovelli, proposes that quantum systems don't have absolute properties. They only have properties relative to other systems. An electron doesn't have a definite position. It only has a position relative to a measuring device. Different observers might experience different realities because they're in different relational contexts. This interpretation suggests that consciousness is not an emergent property of complex matter, but a fundamental feature of reality that plays an active role in determining what exists. The universe might be fundamentally mental in nature, with physical reality emerging from the interaction between consciousness and quantum fields. The consistent histories interpretation, developed by Murray Gell-Mann and James Hartle, proposes that the universe can be described in terms of consistent sets of histories, each with its own probability. Reality consists of all possible histories that are consistent with the laws of quantum mechanics, weighted by their probabilities. This interpretation suggests that the past is not fixed, but exists as a superposition of possibilities until something not necessarily conscious observation selects a specific history. How the universe might be constantly rewriting its own past based on present interactions. The quantum information interpretation, gaining popularity in recent years, suggests that reality is fundamentally informational rather than material. Quantum systems are information processing systems, and physical properties emerge from the way information is encoded and processed in quantum fields. This interpretation aligns with developments in quantum computing and quantum cryptography, suggesting that the universe itself might be a vast quantum computer, processing information and computing reality from moment to moment. Consciousness might be a particular type of information processing that emerges from quantum computational processes. This interpretation suggests that the classical world emerges from the quantum world through a process of information loss. The environment acts as a constant measuring device, destroying quantum coherence and creating the appearance of classical behavior. The environmental decoherence interpretation, developed by Wojciech Surek and others, explains the apparent collapse of quantum states through the interaction of quantum systems with their environment. Quantum coherence is destroyed not by measurement or consciousness, but by the inevitable interaction of quantum systems with the thermal bath of particles and fields that surround them. Each of these interpretations has profound implications for our understanding of consciousness, free will, and the nature of reality. They suggest different answers to fundamental questions. Are we passive observers of a predetermined reality or active participants in its creation? Is consciousness fundamental or emergent? Is reality material or informational? As you drift towards sleep tonight, consider that you might be experiencing reality through the lens of one of these interpretations. Your consciousness might be collapsing quantum states, or selecting from multiple realities, or processing quantum information, or relating to the universe in ways that create the reality you experience. The quantum realm doesn't give us easy answers about the nature of reality. It gives us a rich landscape of possibilities, each as beautiful and mysterious as the others. Perhaps the deepest truth is that reality is large enough to encompass all these possibilities, strange enough to transcend our everyday concepts, and wonderful enough to inspire endless exploration and wonder. This is the quantum vacuum, and it's one of the most profound concepts in all of physics. Far from being empty, the vacuum is actually the lowest energy state of quantum fields, a state that still contains an infinite amount of energy. This energy, called zero-point energy, exists even when all particles have been removed, even when the temperature approaches absolute zero. In the deepest vacuum of space, where every particle has been removed, where no light shines and no sound travels, you might imagine finding perfect emptiness. But quantum mechanics reveals a stunning truth. There is no such thing as empty space. Even in the most perfect vacuum, space itself bubbles with activity, filled with invisible energy and fleeting particles that pop in and out of existence faster than thought itself. In the quiet darkness of your bedroom, you exist at the center of these profound mysteries, your consciousness perhaps playing a role in the ongoing creation of reality itself, participating in the eternal dance between possibility and actuality that defines the quantum universe. To understand why the vacuum must contain energy, we need to think about the uncertainty principle. Remember that energy and time form a complementary pair. You cannot simultaneously know the exact energy of a system and the exact time at which it has that energy. This means that even in the vacuum, the energy is constantly fluctuating, borrowing energy from the future and repaying it so quickly that the debt cannot be detected. These quantum fluctuations are not just theoretical curiosities, they have measurable effects. The Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948, demonstrates that the quantum vacuum exerts real forces on physical objects. When two metal plates are placed very close together in a vacuum, they actually attract each other due to the quantum fluctuations of the vacuum fields. The attraction arises because the quantum fields between the plates are constrained. Only certain wavelengths can fit in the narrow gap. Outside the plates, all wavelengths are possible. This creates a difference in the vacuum energy density, resulting in a net force that pushes the plates together. This force has been measured with extraordinary precision, confirming that the quantum vacuum is indeed filled with energy. The quantum vacuum also explains why atoms don't collapse. In classical physics, electrons orbiting the nucleus should lose energy by radiating electromagnetic waves and spiral into the nucleus. But in the quantum vacuum, the electron constantly interacts with virtual photons, and these interactions provide the energy necessary to maintain stable orbits. The concept of zero-point energy raises profound questions about the nature of reality and energy. If the vacuum contains infinite energy, why don't we observe infinite energy density in the universe? This is one of the deepest puzzles in physics, related to the cosmological constant problem and the nature of dark energy. This interaction with the vacuum also causes tiny shifts in the energy levels of atoms, known as the Lamb shift. These shifts are incredibly small, but they can be measured with extraordinary precision using sophisticated spectroscopic techniques. The agreement between theory and experiment is one of the most precise confirmations of quantum field theory. The quantum vacuum also plays a crucial role in particle physics. Virtual particles, which are temporary excitations of the vacuum fields, mediate all the fundamental forces. The electromagnetic force is carried by virtual photons, the weak nuclear force by virtual Bully and Z bosons, and the strong nuclear force by virtual Gluey. These virtual particles exist for such brief periods that they cannot be directly observed, but their effects are fundamental to the structure of reality. Some scientists speculate that zero-point energy might be the source of dark energy, the mysterious force that's causing the universe to accelerate its expansion. If the vacuum energy density is slightly different from what we expect, it could create the repulsive force that's pushing the universe apart. The vacuum also provides the stage for particle creation and annihilation. When particles and antiparticles annihilate, they don't disappear. They return to the vacuum state. When particles are created, they emerge from the vacuum. In this sense, the vacuum is the womb of all particles, the source from which everything emerges and to which everything returns. Some interpretations of quantum mechanics suggest that the vacuum might be conscious or proto-conscious. If consciousness is related to information processing, and the vacuum is constantly processing quantum information through virtual particle interactions, then perhaps the vacuum itself possesses some form of awareness. Quantum field theory suggests that what we call particles are actually excitations of underlying fields that permeate all of space. The electron field, the photon field, the quark fields, all of these exist even in the vacuum, vibrating at their lowest possible energy states. What we call particles are like waves on the ocean of these quantum fields. The vacuum also exhibits remarkable symmetries and symmetry breaking. The vacuum state has the highest possible symmetry, but as the universe cooled after the Big Bang, these symmetries were spontaneously broken, giving rise to the particles and forces we observe today. The Higgs field, which gives mass to other particles, is thought to have a non-zero value even in the vacuum. In the quiet darkness of your bedroom, the quantum vacuum surrounds you with its invisible energy, its virtual particles, its infinite potential. You rest not in emptiness, but in the most fundamental level of reality, where all possibilities exist and all potentials wait to be actualized. As you drift towards sleep tonight, consider that you are not lying in empty space, but in a sea of quantum activity. The vacuum around you is filled with virtual particles, zero-point fluctuations, and the constant background hum of quantum fields. Your body is not separate from this quantum vacuum. It's a temporary pattern of organization in the same quantum fields that fill all of space. The atoms in your body are constantly interacting with the quantum vacuum, exchanging virtual particles and borrowing energy from the zero-point fluctuations. In the deepest sense, you are not separate from the vacuum. You are the vacuum, temporarily organized in a pattern complex, enough to experience itself as consciousness. In the quantum realm, there exists a strange category of particles that challenge our very notion of existence. These are virtual particles, entities that don't quite exist in the usual sense, yet somehow manage to have very real effects on the world around us. They pop into existence for impossibly brief moments, carry out their quantum business, and then disappear again, leaving behind only their influence on the particles and forces we can actually observe. The more energy that's borrowed, the shorter the time these virtual particles can exist. Massive virtual particles, which require more energy to create, have even briefer lifespans than light virtual particles. A virtual photon might exist for about 10 circumflex 23 seconds, while a virtual crucial boson can only exist for about 10 circumflex 25 seconds. These timescales are so brief that the virtual particles can never be directly observed, yet their effects permeate all of reality. Virtual particles are born from the uncertainty principle's relationship between energy and time. Just as a particle cannot have both a definite position and momentum simultaneously, the universe cannot have both a definite energy and exist at a definite time. This allows the quantum vacuum to borrow energy to create particle-antiparticle pairs, provided these pairs annihilate each other quickly enough that the energy debt is repaid within the time limit set by the uncertainty principle. The strong nuclear force that binds quarks together in protons and neutrons is mediated by virtual gluons. These virtual particles are so fundamental to the structure of matter that they actually contribute most of the mass of protons and neutrons. When you step on a scale, most of your weight comes not from the quarks themselves, but from the energy of the virtual gluons that bind them together. Virtual particles are not just mathematical conveniences, they're the mediators of all fundamental forces. When you feel the electromagnetic force, you're actually experiencing the exchange of virtual photons between charged particles. The electrons in your body are constantly exchanging virtual photons with the protons in your atomic nuclei, creating the electromagnetic bonds that hold your atoms together. Even the weak nuclear force, responsible for certain types of radioactive decay, is mediated by virtual particles, the W and Z bosons. These virtual particles are so massive that they can only exist for extremely brief periods, which is why the weak force has such a short range compared to the electromagnetic and strong forces. Virtual particles also play a crucial role in quantum electrodynamics, the quantum field theory that describes the interaction of light and matter. Every electromagnetic interaction involves the exchange of virtual photons, creating a constant background of virtual particle activity that affects the behavior of all charged particles. This virtual particle activity has measurable consequences. The magnetic moment of the electron, its intrinsic magnetism, is affected by the constant emission and absorption of virtual photons. These corrections have been calculated theoretically and measured experimentally with extraordinary precision, providing one of the most accurate confirmations of quantum field theory. Virtual particles also contribute to the quantum corrections that affect atomic energy levels. The Lamb shift, or the tiny difference between certain energy levels in hydrogen atoms, arises from the interaction of electrons with virtual photons. These interactions are so subtle that they weren't detected until after World War II, when more precise spectroscopic techniques became available. The concept of virtual particles also helps explain the stability of matter. In classical physics, accelerating charges should radiate electromagnetic energy, causing atoms to collapse. But in quantum field theory, the continuous exchange of virtual photons between electrons and nuclei provides the energy necessary to maintain stable atomic structures. Virtual particles even affect the propagation of light through empty space. Photons traveling through the vacuum constantly interact with virtual electron-positron pairs, creating a subtle effect called vacuum polarization. This effect has been measured in high-energy particle physics experiments and confirms our understanding of the quantum vacuum. Perhaps most remarkably, virtual particles can sometimes become real. In intense electromagnetic fields, virtual particle pairs can be promoted to real particles if enough energy is available to pay off their energy debt. This process, called pair production, has been observed in particle accelerators and may occur naturally near black holes and other extreme environments. The boundary between virtual and real particles is not as clear-cut as it might seem. All particles, whether we call them real or virtual, are excitations of the same underlying quantum fields. The distinction is more about whether the particle can be observed directly real or only through its effects, virtual. Some scientists speculate that virtual particles might play a role in consciousness and cognition. If the brain operates partially as a quantum system, then virtual particle interactions in neural microtubules might contribute to the quantum processes that some theories suggest underlie consciousness. Virtual particles also raise profound questions about the nature of causality and existence. If virtual particles can have real effects without really existing, what does this tell us about the relationship between being and becoming, between potential and actual? The concept of virtual particles also suggests that the universe is far more interconnected than classical physics suggests. Every particle is constantly interacting with virtual particles from the quantum vacuum, creating a web of invisible connections that link all things. As you drift towards sleep tonight, consider that your body is continuously bathed in virtual particles. The forces that hold your atoms together, the electromagnetic signals in your nervous system, the quantum processes in your brain, all of these depend on the constant exchange of virtual particles. You are not separate from the quantum vacuum. You are a temporary pattern of organization in the same quantum fields that give rise to virtual particles. Your consciousness might even depend on virtual particle interactions in the quantum networks of your brain. In the quiet darkness of your bedroom, virtual particles are popping in and out of existence all around you, mediating the forces that maintain your body, carrying the electromagnetic signals that sustain your life, and perhaps even participating in the quantum processes that give rise to your dreams. At the deepest level of reality, beneath particles and forces, beneath space and time themselves, lies something even more fundamental: quantum fields. These fields are not made of anything. They are the raw material from which everything else is made. Quantum field theory suggests that what we call particles are actually excitations in these underlying fields, like waves on an infinite ocean, and that space-time itself might emerge from the quantum relationships between these fields. Imagine space as an invisible ocean filled with quantum fields. The electron field permeates every point in space, usually in its lowest energy state. When this field gets excited, we observe what we call an electron. Similarly, the photon field fills all of space, and its excitations are what we call particles of light. Every type of particle corresponds to excitations in its own quantum field. This perspective radically changes how we think about particles. They're not tiny billiard balls moving through space. They're temporary patterns of activity in eternal quantum fields. When a particle is created, it's like a wave rising from the ocean. When it's destroyed, it's like a wave subsiding back into the calm water. The fields remain, but their patterns of excitation change. The mathematics of quantum field theory reveals that these fields are not passive background structures. They actively participate in the creation and destruction of particles. They mediate the forces between particles, and they might even give rise to the geometry of space-time itself. The fields are dynamic, constantly fluctuating, constantly creating and destroying virtual particles that mediate the fundamental forces. This view suggests that what we call empty space is actually the most fundamental level of reality. The vacuum state of quantum fields is not empty. It's the ground state of existence, the lowest energy configuration from which all other phenomena emerge. Particles are excitations above this ground state, like ripples on the surface of an infinitely deep pond. The quantum fields also exhibit remarkable symmetries. The laws of physics look the same if you rotate your coordinate system, if you shift your position in space, or if you change your reference frame. These symmetries are not just mathematical conveniences, they're fundamental principles that determine the structure of reality. But these symmetries can be broken. When the universe was very young and hot, the quantum fields existed in highly symmetric states. As the universe cooled, these symmetries were spontaneously broken, giving rise to the particles and forces we observe today. The Higgs field, which gives mass to other particles, is thought to have acquired a non-zero value throughout space through this process of symmetry breaking. The relationship between quantum fields and space-time is one of the most profound mysteries in physics. Einstein's general relativity describes space-time as a curved manifold with matter and energy determining the curvature. But quantum field theory suggests that space-time itself might emerge from the quantum relationships between fields. Some theories propose that space-time is not fundamental but emergent, that it arises from the entanglement patterns between quantum fields. In this view, the geometry of space and the flow of time emerge from the quantum information shared between different regions of the field. Distance and duration might be derived concepts, emergent from deeper quantum relationships. This emergent space-time picture suggests that the universe is not made of stuff moving through space and time, but of relationships and correlations between quantum fields. The familiar 3 dimensions of space and 1 dimension of time might be low-energy approximations of a more fundamental quantum reality that exists in many dimensions. The quantum fields also provide a natural explanation for the cosmological constant, the energy density of empty space, that might be responsible for the accelerated expansion of the universe. The vacuum energy of quantum fields contributes to this cosmological constant, though the predicted value is vastly larger than what we observe. This discrepancy is one of the greatest puzzles in modern physics. This informational view of quantum fields has profound implications for our understanding of consciousness. If consciousness is related to information processing, and quantum fields are constantly processing information, then perhaps consciousness is not limited to biological brains, but is a fundamental feature of quantum fields themselves. Quantum field theory also suggests that information plays a fundamental role in the structure of reality. The quantum fields can be understood as information processing systems, constantly computing the probabilities and correlations that determine the behavior of particles. The universe might be performing a vast quantum computation, with the field serving as both the hardware and the software. The holographic principle, emerging from studies of black holes and string theory, suggests that all the information in a volume of space can be encoded on its boundary. This principle implies that the 3-dimensional reality we experience might be a hologram projected from information encoded on a 2-dimensional surface. The quantum fields might be the projection mechanism that creates this holographic reality. Some scientists speculate that quantum fields might provide the foundation for a theory of everything, a unified description of all fundamental forces and particles. String theory, loop quantum gravity, and other approaches to quantum gravity all attempt to describe space-time and matter as manifestations of more fundamental quantum field structures. As you drift towards sleep tonight, consider that you are not separate from the quantum fields that permeate all of space. Your body is a temporary pattern of excitation in these eternal fields. Your consciousness might be a particular type of information processing, that emerges from the quantum field dynamics in your brain. The atoms in your body, the forces that hold them together, the electromagnetic signals in your nervous system, all of these are manifestations of quantum field activity. You are not made of particles moving through space. You are space itself, temporarily organized in a pattern, complex enough to experience itself as consciousness. In the quiet darkness of your bedroom, the quantum fields continue their eternal dance, creating and destroying virtual particles, mediating the forces that maintain your body, and perhaps even computing the reality you experience as you drift into sleep. To sleep. As we reach the end of our journey through the quantum realm, we arrive at perhaps the most profound question of all. What is consciousness, and how does it relate to the strange quantum processes we've been exploring? This question touches the very heart of what it means to be human, to be aware, to experience the rich inner world of thoughts, emotions, and sensations that make up your conscious life. The hard problem of consciousness, as philosopher David Chalmers calls it, is not about explaining the brain's functions, how it processes information, controls behavior, or integrates sensory inputs. These are the easy problems of consciousness, difficult as they may be. The hard problem is explaining why there is something it is like to be conscious, why there is an inner subjective experience at all. Why does the firing of neurons in your brain create the felt experience of seeing red or tasting chocolate, or feeling the warmth of sunlight on your skin? Why isn't the brain just a biological computer, processing information without any inner experience? This is the mystery that has puzzled philosophers and scientists for centuries. Some researchers have proposed that quantum mechanics might hold the key to understanding consciousness. The idea is that consciousness might arise from quantum processes in the brain, processes that cannot be explained by classical physics. If consciousness involves quantum phenomena, then it might share some of the strange properties we've been exploring: superposition, entanglement, and the participatory nature of quantum measurement. One of the most famous quantum theories of consciousness was proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that consciousness arises from quantum processes in microtubules, tiny structures within neurons that help maintain the cell's shape and transport materials. According to their theory, these microtubules can maintain quantum coherence for extended periods, allowing quantum computations that give rise to conscious experience. In this view, your consciousness is not just the result of neural firing patterns, but of quantum superposition states in the microtubules of your brain. Your thoughts might exist in quantum superposition before collapsing into definite mental states. The unity of consciousness, the fact that you experience a single integrated stream of awareness despite having billions of neurons, might arise from quantum entanglement between different parts of your brain. The theory also suggests that consciousness might be related to the measurement problem in quantum mechanics. Perhaps conscious observation is what causes quantum wave functions to collapse, making consciousness a fundamental feature of reality rather than an emergent property of complex systems. In this view, you are not just observing reality, you are participating in its creation through the quantum processes of consciousness. Other researchers have proposed that consciousness might be related to quantum information processing. If the brain operates as a quantum computer, then consciousness might be the subjective experience of quantum information integration. The rich, multi-dimensional nature of conscious experience might reflect the high-dimensional quantum state spaces in which the brain operates. But recent research has revealed that quantum effects might be more robust in biological systems than previously thought. Quantum coherence has been observed in photosynthesis, bird navigation, and even in the sense of smell. Some researchers suggest that biological systems might have evolved mechanisms to protect and exploit quantum coherence, making quantum consciousness more plausible. However, the quantum theory of consciousness faces significant challenges. The brain appears to be a warm, wet, noisy environment that would quickly destroy quantum coherence. Critics argue that quantum effects would be too fragile to survive in neural tissue long enough to influence consciousness. The decoherence time for quantum states in the brain is estimated to be far shorter than the timescales relevant for conscious processing. The quantum approach to consciousness, also offers potential solutions to some puzzling features of conscious experience. The binding problem. The binding problem. How the brain combines information from different sensory modalities into a unified conscious experience. The hard problem of qualia. Why subjective experiences have their particular qualities might be explained by the unique quantum signatures of different neural processes. This raises the possibility of quantum immortality, the idea that consciousness might survive the death of the physical brain by existing in quantum states that cannot be destroyed. If consciousness is related to quantum information and quantum information is conserved, then perhaps death is not the end of conscious experience, but a transition to a different form of quantum existence. The quantum theory of consciousness also raises profound questions about the nature of death and personal identity. If consciousness is quantum mechanical, what happens to these quantum states when the brain dies? Some speculate that consciousness might be more fundamental than the physical brain, existing in quantum fields that transcend individual biological systems. The quantum theory of consciousness also suggests that the boundary between self and world might be more fluid than we imagine. If consciousness involves quantum entanglement, then your conscious experience might be fundamentally connected to the quantum processes in your environment. Intum braes and titurs and sirs, Othenderian bears, Sosgerian bears. You might not be separate from the universe. You might be the universe becoming aware of itself through quantum processes. Intum braes and titurs and Derian bears, Sosgerian bears. The mystery of consciousness remains unsolved, but quantum mechanics offers tantalizing hints about its nature. Perhaps consciousness is not just in the universe. Perhaps consciousness is the universe, experiencing itself through the quantum processes that give rise to awareness, thought, and the rich inner life of subjective experience. In the quiet darkness of your bedroom, your consciousness might be a quantum phenomenon, entangled with the deepest levels of reality, participating in the eternal dance between mind and matter, between the observer and the observed, between the quantum and the classical. As you drift towards sleep tonight, consider that your fading consciousness might be a quantum system transitioning between different states. Your dreams might be quantum superposition states, where multiple realities coexist, where the normal collapse of quantum possibilities into definite experiences is relaxed. Imagine trying to find your way through a vast maze. A classical computer would explore each path sequentially, trying one route after another until it found the exit. A quantum computer could explore all paths simultaneously, using the superposition of qubits to represent all possible routes at once. When the quantum computation is complete, the answer emerges from the collapse of these superposition states. Quantum computing represents one of the most exciting frontiers in technology. Unlike classical computers that process information in binary bits, 0s and 1s, quantum computers use quantum bits, or qubits, that can exist in superposition states of both 0 and 1 simultaneously. This allows quantum computers to explore multiple computational paths at once, potentially solving certain problems exponentially faster than any classical computer. As we've explored the strange quantum realm together, you might wonder whether these bizarre phenomena, particles in multiple states, instantaneous connections across vast distances, tunneling through impossible barriers, could ever be more than fascinating curiosities. The answer is a resounding yes. We are on the verge of a quantum technological revolution that will transform computing, communication, and our understanding of what's possible. The potential applications are staggering. Quantum computers could revolutionize drug discovery by simulating molecular interactions with unprecedented accuracy. They could optimize complex logistics problems, from traffic flow to supply chain management. They could break the encryption that protects our digital communications, while simultaneously providing new forms of quantum encryption that are theoretically unbreakable. The challenges of building quantum computers are immense. Quantum states are incredibly fragile, easily destroyed by environmental interference. Quantum computers must be isolated from vibrations, electromagnetic fields, and even cosmic rays. They often operate at temperatures colder than deep space, just fractions of a degree above absolute zero. One of the most promising applications is in artificial intelligence and machine learning. Quantum computers could process vast amounts of data in ways that classical computers cannot, potentially leading to breakthroughs in pattern recognition, natural language processing, and even artificial consciousness. If consciousness itself is quantum mechanical, then quantum computers might be the first artificial systems to exhibit genuine understanding and awareness. Despite these challenges, remarkable progress has been made. Companies like IBM, Google, and IonQ have built quantum computers with dozens of qubits. Google claimed to achieve quantum supremacy in 2019, performing a calculation that would take a classical supercomputer thousands of years to complete. While this particular calculation was artificial, it demonstrated that quantum computers can indeed outperform classical computers for certain tasks. Quantum communication networks are already being deployed. These networks use the principles of quantum entanglement and the no-cloning theorem to create communication channels that are fundamentally secure. Any attempt to intercept quantum communications necessarily disturbs the quantum states, revealing the presence of an eavesdropper. The development of quantum error correction is crucial for building large-scale quantum computers. Quantum errors occur when qubits lose their quantum properties due to environmental interference. Quantum error correction uses multiple physical qubits to encode a single logical qubit, allowing the quantum computer to detect and correct errors without destroying the quantum information. Quantum sensors are another area of rapid development. These devices use quantum effects to achieve unprecedented precision in measuring magnetic fields, gravitational waves, and other physical phenomena. Quantum sensors could revolutionize medical imaging, geological surveys, and fundamental physics research. China has built a quantum communication network spanning thousands of kilometers, using both fiber optic cables and satellite links. Similar networks are being developed in the United States, Europe, and other countries. These networks will eventually form a global quantum internet, enabling secure communication and distributed quantum computing. Distributed quantum communication networks spanning thousands of kilometers. Distributed quantum communication networks spanning satellite links. Similar networks will eventually form a global quantum internet, enabling secure communication and distributed quantum computing. The potential military applications of quantum technology are also significant. Quantum radar could detect stealth aircraft, quantum computers could break enemy encryption, and quantum communication could provide secure military communications. This has led to a global race to develop quantum technologies, with major investments by governments and corporations worldwide. The long-term vision is for quantum computers to become as common as classical computers are today. Quantum smartphones might process information in ways that seem magical to us now. Quantum AI might solve problems that are currently intractable. Quantum simulations might allow us to design new materials, discover new drugs, and understand complex systems from the economy to the climate. Quantum computers might also change our understanding of computation itself. If consciousness is computational, and quantum computers can perform types of computation that classical computers cannot, then quantum computers might be the first artificial systems to exhibit genuine understanding and awareness. But perhaps the most profound implications of quantum computing are philosophical. If quantum computers can simulate quantum systems exactly, they might help us understand the nature of reality itself. They could explore different interpretations of quantum mechanics, simulate the behavior of quantum consciousness, and even test theories about the multiverse. The quantum revolution is also likely to change how we think about privacy, security, and information. In a world where quantum computers can break current encryption, we'll need new forms of security based on quantum mechanics. The quantum internet will enable new forms of distributed computing and communication that are impossible with classical technology. The quantum realm we've been exploring together is not just a curiosity of physics, it's the foundation for technologies that will transform human civilization. Your consciousness, exploring these quantum mysteries, might be preparing you for a future where quantum technology is as natural and ubiquitous as electricity is today. As you drift towards sleep tonight, consider that you might be living through one of the most significant technological transitions in human history. The quantum devices of tomorrow might seem as magical to us as smartphones would have seemed to someone a century ago. As our journey through the quantum realm draws to a close, we find ourselves standing at the edge of the deepest mysteries of existence. Quantum physics has taken us far beyond the familiar world of solid objects and predictable causes, into a realm where the very foundations of reality, space, time, matter, and consciousness, reveal themselves to be far stranger and more wonderful than we ever imagined. In the quiet darkness of your bedroom, the quantum future is already beginning to unfold, promising wonders that we can barely imagine, solutions to problems we haven't yet dreamed of, and a deeper understanding of the mysterious quantum universe that surrounds us. The philosophical implications of quantum mechanics extend far beyond physics into the most fundamental questions of human existence. What is real? What can be known? What is the relationship between mind and matter? These questions, which have puzzled philosophers for millennia, take on new meaning and urgency in light of quantum discoveries. Given to the city of Humenta for quantum discoveries. The quantum realm challenges our most basic assumptions about reality. In our everyday experience, objects have definite properties, whether we observe them or not. A ball is either red or blue, moving or stationary, here or there. But quantum mechanics suggests that particles don't have definite properties until measured. Hall, the act of observation, doesn't just reveal reality, it participates in creating it. This participatory universe raises profound questions about the nature of existence itself. If properties don't exist until observed, then what is the universe when no one is looking? Some interpretations suggest that the universe exists in a state of pure potential, with all possibilities coexisting simultaneously until observation collapses them into definite realities. The role of consciousness in quantum mechanics remains one of the most controversial and fascinating aspects of the theory. If conscious observation is what causes quantum states to collapse, then consciousness becomes a fundamental feature of reality, rather than just an emergent property of complex matter. This suggests that mind and matter are not separate substances, but different aspects of a deeper quantum reality. The quantum realm also challenges our understanding of causality and determinism. In classical physics, the future is determined by the past according to fixed laws, but quantum mechanics introduces genuine randomness into the universe. The future is not completely determined by the past. There are spaces of openness where genuine novelty can emerge. This quantum indeterminacy might be what allows for free will. If our choices are not completely determined by prior causes, then perhaps consciousness can exploit quantum uncertainty to make genuinely free decisions. The quantum processes in our brains might amplify quantum randomness into macroscopic choices, giving us genuine agency in shaping our lives and the world around us. The concept of quantum entanglement also challenges our understanding of space and time. If particles can be instantly connected across vast distances, then perhaps space and time are not as fundamental as we thought. The universe might be more like a hologram, where all information is encoded in every part, rather than a collection of separate objects moving through space.